The Ultimate Java JVM Performance Engineer Masterclass, 210 Production Incidents.
In the world of high-scale enterprise engineering, the Java virtual machine is the engine room of the global economy. From high-frequency trading to global payment gateways, when the JVM falters, business stops. This masterclass is a deep dive into the war room, 210 real-world production incidents where latency spikes, memory leaks, and GC storms translated into millions of dollars in lost revenue. We have designed this to transform you into a staff-level performance engineer, capable of diagnosing the most complex failures under extreme pressure.
The two-part series roadmap, Mastering the 210 JVM Disasters.
To ensure you master both the internal mechanics of the runtime and the external pressures of the cloud, we have divided this masterclass into two deep dive videos. Part 1. Core JVM Internals and Application Mechanics Production Incidents 1 to 131, deep dives into heap memory, GC tuning, CPU hotspots, thread contention, JIT compiler regressions, and the new world of virtual threads project Loom. Part 2. Infrastructure, Distributed Systems and Ecosystem Production Incidents 132 to 210, focusing on Kubernetes resource throttling, Kafka consumer lag, database connection pool exhaustion, and the hidden performance costs of cloud networking and cryptography. Part 1 builds the technical engine. Part 2 secures the enterprise perimeter. Let's begin Part 1.
Part 1. Core JVM Internals and Application Mechanics.
In this first video, we open the hood of the JVM. We will cover 131 production incidents focusing on memory management, execution efficiency, and threading. This is the operational reality of managing thousands of microservices, where a single memory leak can trigger a cascading failure across an entire regional cluster.
Part 1. The Engine Room, Categories 1 to 10 131 Incidents.
We will master the following 10 internal JVM domains in this technical deep dive. Category 1. Heap memory incidents, heap exhaustion, leaks, and retention. Category 2. Garbage collection GC incidents, G1 GC, ZGC, and pause analysis. Category 3. CPU saturation incidents, hotspots, rejects, and serialization. Category 4. Threading and concurrency incidents, deadlocks, and starvation. Category 5. Native memory and off-heap incidents, direct buffers, and metaspace. Category 6. JVM startup, deployment, and JIT incidents, warm-up, and class path scanning. Category 7. JVM crash and fatal error incidents, SIG-SEG and HS_error_PID logs. Category 8. Virtual threads project Loom incidents, pinning and carrier thread starvation. Category 9. Code cache, JIT compiler and GraalVM incidents, deoptimizations, and AOT. Category 10. Dependency, class loading and build pipeline incidents, jar hell, and leaks. 131 production incidents ahead in Part 1. Let's dive into Category 1.
Category 1. Heap memory incidents.
The heap is where your business objects live, but it is also where most production outages begin. In this category, we move beyond simple out-of-memory errors and dive into the high-stakes world of memory retention, allocation pressure, and heap fragmentation. We test your ability to prevent a memory leak from becoming a total platform blackout.
Category 1. Heap memory production incidents 1 to 20.
Here are the first 20 scenarios covering heap exhaustion and retention disasters. Production Incident 1. Out-of-memory error. Java heap space after a 10 times traffic spike. Production Incident 2. Permanent heap growth due to missing cache eviction policies. Production Incident 3. Old generation exhaustion caused by massive JSON deserialization. Production Incident 4. Critical memory leak from unclosed JDBC result sets. Production Incident 5. Security and memory risk via thread local variable retention. Production Incident 6. Heap bloat caused by millions of duplicate string objects. Production Incident 7. Hibernate session retention blocking object cleanup. Production Incident 8. Memory leaks in complex completable future callback chains. Production Incident 9. Batch job commit boundaries causing heap saturation. Production Incident 10. Image processing byte arrays cached permanently in RAM. Production Incident 11. XML DOM parsing loading entire 500 megabytes documents into heap. Production Incident 12. Kafka consumer batch sizes saturating allocation rates. Production Incident 13. Large object allocation failure due to heap fragmentation. Production Incident 14. Cache stampede triggering a sudden allocation explosion. Production Incident 15. Protobuf deserialization overwhelming the young generation. Production Incident 16. Old generation occupancy stuck above 95% threshold. Production Incident 17. Non-stop young Gen GC cycles due to extreme object churn. Production Incident 18. High cardinality micrometer labels exhausting heap memory. Production Incident 19. In-memory aggregation pipelines causing massive heap spikes. Production Incident 20. Heap dump generation filling the production disk storage. Total 20 incidents for heap memory. Let's dive into the troubleshooting deep dive for Production Incident 1.
Production Incident 1. Within 12 minutes of a Black Friday flash sale, your primary checkout microservice starts throwing java.lang. Out of memory error. Java heap space. Throughput has collapsed from 5,000 orders per second to 0, and the business is losing an estimated $85,000 per minute. What is your immediate containment and recovery strategy?
Answer: this is a classic heap exhaustion event caused by unscaled memory settings during a traffic surge. I would handle this via a Tier 1 performance response. 1. Immediate containment. Capture a heap dump using JCMD or JMap on one failing node, then immediately restart the cluster with increased -XMX limits if the underlying hardware allows it to restore service. 2. Root cause analysis. Use Eclipse Mat Memory Analyzer tool to inspect the heap dump. I am looking for incoming references to see if the surge created a massive backlog of order objects that could not be processed fast enough by the downstream payment gateway. 3. Short-term fix. If the heap is saturated with legitimate objects, implement request throttling at the API gateway to keep the JVM within its safe allocation rate until more nodes can be provisioned. 4. Long-term remediation. Tune the -XXG1 reserve % to provide a larger buffer for surges and refactor the checkout flow to use a streaming approach rather than loading the entire order object graph into memory. Pro tip: in high-traffic scenarios, is often a symptom of downstream latency. If your payment provider slows down, your JVM heap fills up with waiting objects. Always implement a circuit breaker to drop traffic before the heap hits 90% to avoid a total platform crash.
Production Incident 2. Your global pricing service is experiencing a slow motion crash. Every 6 hours, the heap usage reaches 98%, triggering a full GC that freezes the app for 30 seconds and causes thousands of HTTP 504 gateway timeouts. You discover that a developer implemented a custom pricing cache using a hash map, but forgot to add an eviction policy. How do you resolve this architectural leak?
Answer: this is a resource retention failure caused by an unbounded collection. I would immediately replace the raw hash map with a structured caching library like Caffeine or Guava, enforcing a maximum size or time to idle TTI eviction policy to ensure the oldest entries are purged. If I cannot change code immediately, I would use a stopgap measure by reducing the -XX initiating heap occupancy % to trigger GC earlier, though this only delays the inevitable. The permanent fix is to ensure that the cache uses soft references so the JVM can reclaim the memory under pressure rather than throwing an Pro tip: never use a static hash map as a cache in production. Even if you think the data is small, schema drift or product growth will eventually turn it into a memory bomb. Always use a professional caching library with size-based eviction from day one.
Production Incident 3. A partner API began sending 50 megabytes bulk transaction JSON payloads to your ingester. Your JVM is crashing with old-gen exhaustion because the Jackson object mapper is creating millions of intermediate objects during deserialization, which are being promoted to the old gen almost instantly. How do you re-architect the ingestion?
Answer: this is an allocation pressure issue where large objects are bypassing the young generation. My remediation plan is: 1. Root cause analysis. The JSON payload size exceeds the G1 humongous object threshold, causing these objects to be allocated directly in the old generation, leading to rapid fragmentation and CMS or G1 failure. 2. Immediate fix. Increase the -XXG1 heap region size to 32 megabytes to ensure more objects fit into the young generation regions, allowing them to be cleaned up by minor GCs. 3. Long-term remediation. Rewrite the ingestion logic to use the Jackson Streaming API JSON parser. This allows you to process the 50 megabytes file token by token with a constant memory footprint of only a few kilobytes. Pro tip: Object Mapper is convenient but dangerous for large payloads. In JVM engineering, streaming is king. If you can process data as a stream, you can handle a 1 gigabytes file with a 1 gigabytes heap without ever triggering a full GC. Here is Java code demonstrating the shift from a memory-intensive object mapper to the Jackson Streaming API to process large payloads without heap saturation. Disclaimer: always test code in a non-production environment by using JSON parser instead of loading the entire input stream into a single object mapper call. We avoid the massive intermediate object allocation that causes old-gen exhaustion. We still use the mapper for convenience, but only to deserialize one small object at a time. This keeps the memory footprint flat regardless of whether the JSON is 5 megabytes or 500 megabytes.
Production Incident 4. After 48 hours of uptime, your legacy banking service crashes. Analysis of the heap dump shows that 70% of the memory is occupied by JDBC result set objects. It appears a developer is closing the connection, but failing to close the result set or statement in a high-frequency loop. How do you stop the leak?
Answer: this is a native resource leak where Java heap objects are acting as wrappers for unreleased database cursors. I would fix this through the following steps. 1. Root cause analysis. Unclosed result sets keep a reference to the internal session state, preventing the GC from reclaiming the memory until the physical connection is closed by the pool. 2. Immediate remediation. Force a pool reset in your connection pool, for example, Hikari CP, to kill the long-lived connections and free the associated native and heap memory. 3. Code fix. Refactor the DAO layer to use try with resources for all JDBC objects. This guarantees closure even if an exception occurs mid-loop. Pro tip: modern frameworks like Spring Data JPA handle this for you, but in vanilla JDBC or legacy Hibernate, this is a top 3 cause of production crashes. Always use try with resources. It is the only way to be 100% safe. Here is Java code demonstrating the use of try with resources to ensure automatic closure of JDBC resources and prevent native memory leaks. Disclaimer: always test code in a non-production environment. This syntactic sugar ensures that the connection, prepared statement, and result set are all closed in the correct order, even if the processing logic throws a runtime exception.
Production Incident 5. An audit reveals that sensitive customer session objects are appearing in heap dumps of unrelated threads. Further investigation shows that a thread local variable was used to store user context, but was never removed. This is causing both a catastrophic memory leak and a major GDPR data leakage risk. What is your strategy?
Answer: this is a thread pollution incident. Because threads in a servlet container are reused, a thread local value set during one request will bleed into the next request if not explicitly cleared. I would immediately implement a global servlet filter that calls .remove on all thread local variables in a finally block after every request to sanitize the thread. For modern Java 21 plus apps, I would migrate the team toward using scoped values, which are immutable and have a strictly defined automatic lifetime. Pro tip: thread locals are silent killers. If you must use them, always wrap the logic in a try finally block. If you do not call .remove, you are not just leaking memory, you are potentially serving customer A's data to customer B.
Production Incident 6. A customer analytics service is consuming 12 gigabytes of RAM despite only processing 1,000 active users. A heap dump reveals that 40% of the heap is taken up by the exact same country name and currency code strings repeated millions of times. How do you optimize this bloat?
Answer: this is a string redundancy issue. I would implement string deduplication and reference management to reclaim the memory. 1. Immediate JVM fix. Enable JVM level deduplication by adding the flags -xx plus use G1 GC -xx plus use string deduplication. This allows the GC to point duplicate char arrays to a single instance automatically. 2. Code optimization. Use string.intern for a small, known set of constants, but be cautious of the string table size limits. 3. Architectural fix. Implement a canonical map. Instead of creating a new string for every database row, use a local map to store unique values and reuse the existing reference when a duplicate is encountered. Pro tip: JVM string deduplication is a free performance win in G1GC, but it only works on strings that have reached the old generation. For young gen bloat, you must fix the code to reuse references manually.
Production Incident 7. Your ERP tool crashes every Friday during the payroll run. The heap dump shows millions of managed entities being held by the Hibernate persistence context. The developer is processing 100,000 employees in a single transactional method, causing the system to run out of memory before the final commit. How do you fix the commit boundary?
Answer: this is a transaction scope failure where the Hibernate session is acting as a memory leak. I would refactor the batch process as follows. 1. Root cause analysis. Hibernate maintains a first-level cache of every object loaded. Processing 100,000 employees in one block keeps them all in RAM until the method returns, exhausting the heap. 2. Immediate fix. Manually call entitymanager.flush and entitymanager.clear every 500 records to synchronize changes and detach the objects from the heap. 3. Stateless option. For read-heavy payroll calculations, use a stateless session in Hibernate, which bypasses the first-level cache entirely and reduces memory overhead by 90%. Pro tip: in Hibernate, the session is the leak. Never perform mass updates inside a single transaction. If your session holds more than 1,000 entities, you are risking an and causing massive database lock contention. Here is Java code showing how to manually manage the Hibernate persistence context to prevent session-level memory bloat during mass batch updates. Disclaimer: always test code in a non-production environment. By clearing the entity manager periodically, we detach processed entities from the persistence context, allowing the garbage collector to reclaim their memory before the transaction ends.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 8. A high-throughput reactive gateway is crashing with Profiling shows that thousands of completable future objects are staying in memory for minutes. You discover a chain reaction where one slow external API is causing a backlog of callback lambdas that retain the entire request and response object graphs. How do you break the chain?
Answer: this is a callback retention failure. The completable future chain keeps a hard reference to every object in its scope until the final stage completes. I would first implement strict timeouts using dot or timeout to ensure no future stays alive longer than a few seconds. I would then refactor the lambdas to only capture the request ID rather than the entire object graph. allowing the larger objects to be garbage collected while the async task is waiting for the I/O to return. Pro tip: in async Java, scope is sticky. Be extremely careful about what variables your lambdas capture. If a lambda captures a large object, that object is immortal until the async task finishes or times out. Here is Java code demonstrating how to minimize lambda capture scope in async pipelines to prevent large object graphs from being retained in the heap. Disclaimer: always test code in a non-production environment by extracting only the ID into a local variable. The lambda only captures the small string reference instead of the entire multi-megabyte request object graph. Enforcing a timeout ensures that even if the external system hangs, the future and its captured variables are cleared within a predictable window.
Production Incident 9. A nightly data migration job is saturating the heap and triggering GC, thrashing 95% CPU spent on GC. You realize the list used to buffer the data is growing to 1 million records before a single database write occurs. How do you stabilize the buffer?
Answer: this is an unbounded buffer failure. I would implement a producer-consumer pattern with strict backpressure to keep the heap footprint constant. 1. Immediate fix. Implement a flush threshold in the existing code to trigger a database batch insert and call .clear on the list every 1,000 records. 2. Architectural remediation. Transition to a blocking queue with a fixed capacity. If the queue is full, the CSV reader is forced to wait, providing natural backpressure. 3. JVM tuning. For this batch workload, use -XX plus use parallel GC to prioritize total throughput over individual pause times. Pro tip: unbounded lists are the #1 cause of batch job failures. Always use a sized buffer or a streaming iterator to ensure your memory footprint remains flat regardless of data volume. Here is Java code showing the implementation of a bounded blocking queue to provide natural backpressure and stabilize heap usage during data migrations. Disclaimer: always test code in a non-production environment. A bounded queue is the simplest architectural pattern to enforce backpressure. It prevents the producer from saturating the heap while the consumer is waiting for the database.
Production Incident 10. Your medical imaging portal is crashing under heavy load. A heap dump shows that byte arrays representing raw images are filling 90% of the heap. It turns out the image thumbnail service is caching these raw bytes in a static map to save time. How do you fix this resource mismanagement?
Answer: this is a heavy asset retention failure. Caching raw byte arrays in the heap is dangerous because it triggers humongous allocations in G1 GC, leading to premature full GCs. I would immediately move these images off heap using an external cache like Redis or a direct byte buffer for local storage. If an in-memory cache is absolutely required, I would use a library like Caffeine with a weighted eviction policy based on the total bytes stored, ensuring the cache shrinks automatically before the JVM runs out of memory. Pro tip: never cache big data images, videos, large PDFs inside the JVM heap. The GC is not designed to manage multi-megabyte arrays efficiently. Use off-heap memory or external storage to keep your JVM lean and mean.
Production Incident 11. A nightly financial reporting service is crashing with every time it processes a large XML invoice from a Tier 1 vendor. The heap dump shows that the XML DOM parser is loading the entire 500 megabytes document into the heap, creating a massive tree of 4 million node objects. How do you re-architect the parser?
Answer: this is a DOM tree exhaustion incident. I would migrate the parsing strategy to a streaming model to maintain a flat memory footprint. 1. Root cause analysis. The document object model DOM is an in-memory representation. For a 500 megabytes file, the heap overhead can be 5 times to 10 times the raw file size due to object metadata. 2. Immediate fix. Increase the container memory temporarily to allow the report to finish. But this is not a scalable solution. 3. Long-term remediation. Implement a stack streaming API for XML or SAX parser. These are event-driven and only keep the current element in memory, allowing you to process multi-gigabyte files with a 64 megabytes heap. 4. Governance fix. Implement a file size guardrail in the ingestion layer to reject any XML larger than 100 megabytes if it hasn't been routed to the streaming optimized pipeline. Pro tip: DOM is for search and edit. Stacks is for read and process. If you are only extracting data to a database, never use DOM. Stacks gives you the control of a stream with the performance of a pull model. Here is Java code demonstrating the shift from DOM to Stacks XML Stream Reader to process large XML documents with constant memory usage. Disclaimer: always test code in a non-production environment. This code initializes the streaming reader, which pulls data from the source only as needed, rather than loading the entire file into a heap-based tree. Here is the code using event-based logic to identify specific tags. This ensures that only the current node is active in RAM at any given time.
Production Incident 12. Your order processing Kafka consumer is experiencing massive lag, and the JVM is hitting 98% heap occupancy. You discover that the max.poll.records is set to 5,000, and every order object is 100 kilobytes, causing the young generation to be bypassed and saturating the old generation with every poll. How do you stabilize the consumer?
Answer: this is a batch size or heap mismatch. When the combined size of a Kafka poll exceeds the available Eden space, or the G1 region size, the JVM performs humongous allocations directly into the old gen. I would immediately reduce max.poll.records to 500 and tune fetch.max.bytes to ensure each batch fits comfortably within the young generation. This allows the GC to clean up the batch objects in a micro-pause rather than triggering a stop-the-world full GC. Pro tip: Kafka tuning is often JVM tuning in disguise. If your max.poll.records average _record size is greater than 25% of your young gen, you are guaranteed to have GC-related throughput collapse.
Production Incident 13. Your high-frequency trading JVM crashes with even though the total free heap is reported as 2 gigabytes. The error log shows full GC allocation failure while trying to allocate a large 50 megabytes byte array. How do you diagnose and fix this invisible memory failure?
Answer: this is a heap fragmentation incident where there is enough total space, but no single contiguous block large enough for a humongous object. 1. Diagnosis: run jstat-gc calls and check for G1 humongous allocation failures. If the old gen is fragmented, the GC cannot find enough adjacent regions to satisfy the request. 2. Immediate tuning: increase the -XX G1 heap region size, for example, to 16 megabytes or 32 megabytes. Larger regions reduce the chance of an object being classified as humongous. 3. Code fix: refactor the 50 megabytes array into a list of smaller buffers or use an off-heap direct byte buffer. This prevents the requirement for massive contiguous blocks in the managed heap. 4. Long-term remediation: enable -XXG1 mix GC live threshold % to trigger mix GCs earlier, which helps compact the heap more aggressively before fragmentation becomes critical. Pro tip: fragmentation is the silent killer of long-running JVMs. If your application allocates large arrays frequently, G1 GC will eventually fragment. Moving these allocations off heap is the only permanent architectural solution.
Production Incident 14. Following a brief database network flicker, your JVM experienced a cache stampede. 50,000 concurrent threads attempted to repopulate an expired product metadata cache simultaneously, creating 50,000 duplicate objects and crashing the heap. How do you prevent this allocation explosion?
Answer: this is a concurrency-induced allocation failure. To resolve this, I would implement coalesced loading using a synchronized loader or the compute if absent method in a concurrent hash map. This ensures that only the first thread is allowed to fetch data from the database and populate the cache, while all other threads block and wait for that single result, effectively reducing the allocation pressure from 50,000 objects to just one. Pro tip: never use get then put logic for cache loading. Always use a loading cache pattern like caffeine that provides single flight guarantees. It protects both your JVM heap and your downstream database from being crushed during a cold start. Here is Java code demonstrating the loading cache pattern to prevent cache stampedes and redundant heap allocations under high concurrency. Disclaimer: always test code in a non-production environment. This code defines the loading logic inside the cache itself, ensuring that even if 1,000 threads ask for the same key, The database is only called once. Here is the code where threads wait for the shared result. This prevents the allocation explosion of creating duplicate objects for the same key across 1,000 threads.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 15. A microservices cluster using protobuf for serialization is seeing 200 milliseconds latency spikes. JFR Java Flight Recorder shows that massive protobuf deserialization is creating thousands of short-lived objects that are prematurely promoting to the old gen because the survivor space is too small. How do you optimize the object lifecycle?
Answer: this is a survivor space overflow incident. The objects are overflowing into the old gen before they have a chance to die in the young gen. 1. Root cause. The high-frequency deserialization creates a burst of objects. If Eden plus survivor is smaller than the burst, the JVM tenures them immediately to the old generation. 2. Tuning fix. Increase the -XX survivor ratio, or manually set a larger -XM in young gen size to ensure that the survivor spaces can hold the entire deserialization burst. 3. Code optimization. Switch to protobuf Java util with reused message builders where possible to reduce the total number of allocation events per request. 4. Verification. Use JStat-GC to monitor the promotion rate. If the OU old gen usage increases during every load test, your survivor spaces are still too small. Pro tip: performance engineering is about keeping short-lived objects in the young generation. If your young gen is too small, your old gen will fill up with garbage, leading to expensive and unnecessary full GCs.
Production Incident 16. Your recommendation engine is sluggish, and monitoring shows the old generation occupancy is stuck at 96%, even after a full GC. The JVM is spending 40% of its CPU just trying to find a few kilobytes of space. What is your emergency triage for near full old generation?
Answer: this is GC thrashing caused by a live lock. The heap is full of live objects that the GC cannot reclaim, but there is just enough space to avoid a hard I would immediately take a heap dump to identify which cache or session store has grown too large. As an emergency fix, I would decrease the -XXG1 mixed GC live threshold percent to 60% to force the JVM to clean up regions with more live data, which might reclaim enough space to stop the CPU thrashing until I can fix the underlying memory leak. Pro tip: when old gen occupancy stays above 90%, your JVM is effectively dead even if it hasn't crashed yet. The CPU cost of managing a nearly full heap is often higher than the cost of a clean restart.
Production Incident 17. An ad tech bidding platform is experiencing extreme object churn. The application creates 4 gigabytes of temporary objects every second, causing G1 GC to run minor collections every 200 milliseconds, which is killing the bidding throughput. How do you reduce allocation pressure?
Answer: this is an object churn incident where the cost of allocation and collection is higher than the business logic execution. 1. Code analysis. Use a sync profiler with the alloc event to find the exact line of code responsible for the 4 gigabytes per second churn. Usually, it is a string plus string concatenation in a tight loop or an inefficient JSON mapper. 2. Refactoring. Replace string concatenation with string builder or move to a zero allocation library like Agrona if the churn is coming from primitive to object boxing. 3. Tuning. Increase the young generation size dramatically, for example, to 60% of total heap to allow the GC to batch these collections less frequently, reducing the pause to throughput ratio. 4. Escapism. Check if escape analysis is failing. If the JVM cannot prove an object does not leave the method, it cannot perform stack allocation, forcing every object onto the heap. Pro tip: the fastest GC is the one that never runs. Before tuning GC flags, always look for hidden allocations like auto-boxing integer versus int or enum dot values calls in loops, which generate massive amounts of garbage for no reason.
Production Incident 18. A metrics update caused an crash in the payment gateway. You discover that a developer added a customer_ID tag to a micrometer counter. Since you have 5 million unique customers, the JVM created 5 million unique meter objects in the heap. How do you resolve high cardinality metrics bloat?
Answer: this is a metadata leak caused by cardinality explosion. Every unique combination of tags in micrometer creates a new object in the internal registry that is never garbage collected. I would immediately revert the change and implement a metrics filter to block the customer_ID tag. For future tracking, I would move high cardinality data, like user IDs, to the distributed tracing layer like OpenTelemetry or structured logs, which are designed for high cardinality data, keeping the JVM metrics registry limited to low cardinality operational data like region or HTTP status. Pro tip: never put IDs, customer, order, session in metrics tags. Metrics are for aggregates, logs or traces are for individuals. A single high cardinality tag can bring down a 32 gigabytes JVM in minutes.
Production Incident 19. An in-memory aggregation pipeline is causing massive heap spikes when processing the end-of-month data. You find that the code is using stream.collect with collectors.toList to group 10 million records in memory before calculating the average. How do you stabilize the memory footprint?
Answer: this is a materialization failure where the entire dataset is being held in a list unnecessarily. I would refactor to a single pass reduction. 1. Root cause. Collectors.toList forces every object to stay in the heap. For 10 million records, this creates a massive memory peak that exceeds the heap limit. 2. Code fix. Use terminal reductions like collectors.summarizing long or collectors.averaging double. These calculate the result incrementally and do not store the individual objects in a list. 3. Alternative. Use a parallel stream with a custom accumulator to distribute the memory load across multiple threads, though single pass reduction is usually safer for memory stability. 4. Governance. Implement a stream limit or pagination at the source to ensure that no single JVM thread attempts to aggregate more than 1 million records in a single pass. Pro tip: collect is the most dangerous word in the stream's API. If you do not need the individual objects later, never use .toList. Always reduce or aggregate on the fly to keep your heap usage near zero. Here is Java code demonstrating the shift from memory-intensive list collection to a single-pass streaming reduction for large-scale data aggregation. Disclaimer: always test code in a non-production environment. This code uses the summarizing collector to calculate the count, sum, min, max, and average simultaneously as the stream flows, without storing a single order object in a collection. Here is the code extracting the result. By avoiding the intermediate list, we reduce the heap requirement from gigabytes to bytes for the same calculation.
Production Incident 20. During a critical outage, An SRE attempted to generate a heap dump jmap-dump:live to find a memory leak. However, the 16 gigabytes heap dump completely filled the production disk, causing the application to crash and the Kubernetes node to be evicted. How do you perform safe diagnostics in production?
Answer: this is an observability-induced failure. I would implement a safe dump strategy by always pointing the heap dump path to a dedicated diagnostic volume that is separate from the application's root disk. I would also use the -XX plus heap dump on out-of-memory error flag with a pre-configured -XX heap dump path to ensure the dump is only captured when necessary. To minimize the risk, I would move toward low-overhead diagnostics like JFR Java Flight Recorder or heap histograms jcmd_gc.class_histogram, which provide 80% of the value of a heap dump with 1% of the disk and CPU overhead. Pro tip: a heap dump is a one-to-one copy of your RAM. If you have a 32 gigabytes heap, you need 32 gigabytes of free disk space. Never run a manual heap dump in production without verifying the df-h status of your target volume first.
Category 1 Conclusion: Mastering the managed heap.
Mastering Java heap memory is the foundation of JVM stability. As we've seen in these first 20 incidents, the difference between a high-performing system and a production crash often comes down to how you manage object retention and allocation boundaries. Whether it is shifting from DOM to stacks for XML or enforcing backpressure with bounded queues, the goal is clear. Keep the heap footprint flat and predictable. If you control the allocation, you control the uptime.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 1 to Category 2.
But even with perfectly optimized code, your application is at the mercy of the cleaning crew, the garbage collector. If the heap is where your data lives, the GC is the engine that decides when that data dies. When the GC falters, it does not just slow down your app, it stops the world. We now move from the storage of the JVM to its metabolism. Garbage collection, GC architecture, and tuning failures. Let's explore Category 2.
Category 2. Garbage collection GC incidents.
Garbage collection is the heartbeat of the JVM, but a single tuning error can turn a minor cleanup into a 45-second platform freeze. In this category, we dive into G1GC, ZGC, and the legacy CMS collectors. We will analyze the stop-the-world events that cause socket timeouts, duplicate payments, and Kubernetes readiness failures. We test your ability to tune the collector for the impossible balance. Maximum throughput versus minimum latency.
Category 2. Garbage collection production incidents 21 to 40.
Here are the 20 scenarios covering GC-driven platform collapses and tuning disasters. Production Incident 21. Full GC pauses exceeding 45 seconds in the payment gateway. Production Incident 22. GC thrashing consuming 90% CPU and halting order processing. Production Incident 23. G1 GC humongous allocations causing regional heap fragmentation. Production Incident 24. CMS concurrent mode failure triggering stop the world emergencies. Production Incident 25. Promotion failures leading to repeated, cascading full GCs. Production Incident 26. Survivor space misconfiguration causing premature object promotion. Production Incident 27. Incorrect young generation sizing increasing pause frequency. Production Incident 28. GC tuning regressions causing 15% throughput drop after deployment. Production Incident 29. Massive 64 GB heaps amplifying pause times beyond SLA limits. Production Incident 30. Compressed OOPS threshold exceeded causing 20% memory bloat. Production Incident 31. ZGC migration causing unexpected latency instability in low load periods. Production Incident 32. GC log rotation disabled, leading to disk exhaustion and node crashes. Production Incident 33. Full GC pauses triggering Kubernetes readiness probe failures. Production Incident 34. Excessive allocation rates overwhelming the G1 collector capacity. Production Incident 35. Heap occupancy alarms ignored until the JVM hit a terminal freeze. Production Incident 36. Transparent huge pages THP increasing GC pause tail latency. Production Incident 37. G1 mixed collections becoming ineffective due to high live data density. Production Incident 38. Old generation fragmentation causing intermittent allocation stalls. Production Incident 39. JVM SafePoint sync times increasing unexpectedly during GC cycles. Production Incident 40. Manual GC tuning implemented without a proper baseline workload analysis. Total 20 incidents for garbage collection. Let's start with Production Incident 21.
Production Incident 21. During a high load event, your primary payment gateway experienced a stop the world full GC pause that exceeded 45 seconds. This caused downstream microservices to hit socket timeouts, triggering a retry storm that resulted in $120,000 in duplicate customer charges. How do you resolve this latency disaster?
Answer. This is a pause time SLA violation. I would immediately analyze the GC logs to determine if the 45-second pause was caused by G1 GC failing to find enough free regions allocation failure. I would decrease the -XX max GC pause millis target to 200 milliseconds and increase the -XX G1 reserve percent to 15% to provide a safety buffer for sudden bursts. This ensures the JVM triggers concurrent cycles earlier, preventing the stop the world event that crippled the payment flow. Pro tip. A 45-second pause is usually a failure to evacuate. It means your GC was so behind that it had to stop everything to compact the heap. Never trust the default GC settings for payment systems. Always set a hard pause time goal and provide a 10 to 20% reserve heap space to handle spikes.
Production Incident 22. Your order orchestration service is showing 100% CPU usage, but business throughput has dropped to near zero. Monitoring reveals the JVM is in a state of GC thrashing, where 90% of CPU cycles are spent on garbage collection. How do you recover the service?
Answer. This is a live-lock scenario where the JVM is working hard but achieving nothing. I would execute this recovery plan. 1. Immediate action. Drain traffic from the affected node and capture a GC log and thread dump. The high CPU is likely due to thousands of GC worker threads constantly scanning a nearly full heap. 2. Root cause analysis. Check if the live set memory remaining after full GC is greater than 85% of total heap. If it is, the JVM simply does not have enough room to operate, regardless of tuning. 3. Remediation. Increase the -XMX heap size immediately. If hardware is at its limit, you must scale out the cluster more nodes to reduce the per-node allocation rate to a level the GC can handle. 4. Prevention. Implement an automatic kill switch using -XX+, exit on out-of-memory error, or a custom SRE script that restarts a node if time spent in GC exceeds 20% over a 5-minute window. Pro tip. GC thrashing is the walking dead state of a JVM. It consumes all your CPU credits but processes no requests. Always monitor the GC overhead metric. If it hits 10%, you are minutes away from a total platform collapse.
Production Incident 23. An image resizing service using G1 GC is crashing intermittently without memory error. Java heap space. GC logs show that humongous allocations are fragmenting the heap regions, making it impossible for the GC to find contiguous space even when 4 GB is reported free. How do you fix the fragmentation?
Answer: this is a region fragmentation incident caused by objects larger than 50% of the G1 region size. I would optimize the region architecture. 1. Root cause. Large byte arrays from images are being classified as humongous and allocated directly in the old generation, which does not compact as efficiently as the young generation. 2. Immediate tuning. Increase the -XXG1 heap region size to 16 megabytes or 32 megabytes. This reclassifies many humongous objects as regular objects, allowing them to be managed in the young gen. 3. Code fix. Refactor the image processing to use a buffer pool or streaming approach, avoiding the creation of single, massive byte arrays in the heap. 4. Monitoring. Use jcmd.pidgc.heap_info to track the number of humongous regions. If they exceed 10% of the total heap, your region size is too small. Pro tip: G1 GC loves tiny objects. If you frequently allocate arrays larger than 1 megabytes, G1 GC will fragment your heap. Raising the region size to 32 megabytes is the standard quick fix for image and document processing services. Here is JVM configuration, demonstrating how to increase the G1 region size to prevent heap fragmentation from humongous objects. Disclaimer: always test code in a non-production environment. This code explicitly sets the region size. By increasing this value, objects that were previously considered humongous are now treated as normal, allowing the GC to manage them without fragmenting the old generation.
Production Incident 24. Your legacy inventory system is running on the CMS concurrent mark sweep collector. You see a sudden spike in concurrent mode failure in the logs, followed by a 15-second stop the world pause that timed out the database connection pool. What is your emergency tuning for CMS?
Answer: a concurrent mode failure happens when CMS cannot finish cleaning the old gen before the young gen tries to promote more objects. I would immediately decrease the -XX CMS initiating occupancy fraction to 65 and set -XX plus use CMS initiating occupancy only to true. This forces the GC to start its concurrent cycle much earlier, ensuring there is always enough headroom in the old gen to accept new promotions even during a traffic spike. Pro tip: CMS is a fine-tuned race between the application and the collector. If you wait until the heap is 90% full to start cleaning, you will lose that race. Starting at 65% occupancy is the safest configuration for high-velocity legacy apps.
Production Incident 25. A loyalty point service is trapped in a cycle of promotion failures. Every time a minor GC runs, it attempts to move objects to the old generation, fails, and triggers a full serial GC pause of 10 seconds. This happens 5 times every hour. How do you break the cycle?
Answer: this is a promotion failure crash loop. I would resolve it by increasing old gen headroom and slowing down promotion. 1. Root cause. The old generation is so fragmented or full that it cannot accommodate a contiguous promotion from the young gen, forcing the JVM to stop everything for a compacting full GC. 2. Immediate fix. Increase the -XMX to give the old gen more space. If RAM is limited, reduce the young gen size -XMN to reduce the volume of each individual promotion attempt. 3. Tuning. Adjust -XXG1 mixed GC live threshold % for G1 to 60% to force the JVM to clean old gen regions more aggressively. 4. Verification. Monitor the promotion rate in your APM. If it spikes during specific jobs, you need to refactor those jobs to stop creating long-lived objects. Pro tip: promotion failure is usually a sign that your old generation is too small relative to your young generation. The rule of thumb is that the old gen should be at least 2 times the size of the young gen to safely handle promotions.
Production Incident 26. You observe that objects are being tenured moved to old gen after only 1 second of life, even though they should be dying in the young gen. This premature promotion is filling your old gen with garbage and causing full GCs every 30 minutes. How do you fix the survivor spaces?
Answer: this is a survivor space overflow. The young gen is leaking garbage into the old gen. I would implement the following tuning. 1. Diagnosis. Use JStat-GC to check the age of objects in the survivor space. If objects are reaching the tenuring threshold too quickly, the survivor space is too small to hold the current workload burst. 2. Tuning fix. Increase the -XX max tenuring threshold up to 15, and increase the -XX survivor ratio to give the JVM more room to keep middle-aged objects in the young gen. 3. Scale fix. Increase the total young gen size -XX new size to ensure the total Eden plus survivor capacity is greater than your peak request object volume. 4. Validation. Ensure that the old generation usage remains flat after minor GCs. This proves that objects are correctly dying in the young gen. Pro tip. Most developers ignore survivor spaces, but they are the filter of the JVM. If your filter is too small, your engine old gen will get clogged with garbage. Setting max tenuring threshold equals 15 is the gold standard for microservices. Here is JVM configuration showing how to tune tenuring thresholds and survivor ratios to prevent premature object promotion. Disclaimer: always test code in a non-production environment. This code sets the maximum age an object can reach in the young generation before being promoted. Setting this to 15 maximizes the chance that temporary objects will die before hitting the old gen. Here is the code telling the JVM to use 90% of the survivor space before initiating promotion. This prevents the overflow that occurs when the default 50% threshold is reached too early.
Production Incident 27. A search API is experiencing latency spikes every 10 seconds. You find that the young generation is sized at only 256 megabytes on a 16 gigabytes heap, causing minor GCs to run so frequently that the SafePoint overhead is visible in your application metrics. How do you resize the generations?
Answer: this is a sizing imbalance. When the young gen is too small, the JVM spends all its time in minor GC cycles, which still require a world stop pause. I would immediately increase the young generation to at least 4 gigabytes, roughly 25 to 30% of total heap. This reduces the GC frequency from every 10 seconds to every 2 minutes, allowing the application to spend more time on business logic and less time synchronizing threads for the collector. Pro tip: a small young gen is the #1 cause of death by 1,000 cuts. You might not see a 10-second pause, but 100 mini pauses of 100 milliseconds each will destroy your API throughput just as effectively.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 28. After a performance optimization deployment where you changed 5 GC flags, the application's overall throughput dropped by 15%. Your 99th percentile latency improved, but the total number of process transactions per second decreased. How do you roll back or fix this?
Answer: this is a throughput versus latency trade-off failure. I would handle this by re-evaluating the goals of the tuning. 1. Root cause. You likely moved from a throughput collector parallel GC to a latency collector G1 GC, or set the -XX max GC pause mill is too low, forcing the JVM to spend more CPU on frequent small GCs. 2. Remediation. Remove the aggressive -XX max GC pause millas and allow the JVM more slack to process larger batches. This reduces the total CPU overhead spent on GC management. 3. Data-driven fix. Use JFR Java Flight Recorder to compare the time spent in GC between the two versions. If version B spent 20% more time in GC, the optimization was actually a regression. 4. Rule of thumb. Never tune more than 2 GC flags at once. GC tuning is a nonlinear science. Changing 5 things simultaneously makes it impossible to identify the culprit. Pro tip: low latency is not free. It always costs throughput. In enterprise systems, you must decide: do I want every request to be fast latency, or do I want to process the most requests possible throughput? Here is JVM configuration, demonstrating a rollback from aggressive latency tuning to balanced throughput settings. Disclaimer: always test code in a non-production environment. This code increases the pause target. By allowing the GC 250 milliseconds instead of 50 milliseconds, we reduce the frequency of collections, giving the CPU back to the application logic to restore throughput.
Production Incident 29. Your big data processing node has 128 gigabytes of RAM. Using G1 GC, your pause times are exceeding 5 seconds because the JVM has to scan millions of objects. How do you handle large heap latency in 2026?
Answer: G1 GC is not efficient for heaps larger than 32 gigabytes due to the overhead of region management and scanning. I would immediately migrate this node to ZGC0 garbage collector. ZGC is a concurrent collector that performs almost all of its work while the application threads are running, keeping pause times under 10 milliseconds regardless of whether the heap is 128 gigabytes or 12 terabytes. This would instantly eliminate the 5-second stop-the-world spikes and restore predictable performance. Pro tip: if your heap is greater than 32 gigabytes, G1 GC is the wrong tool. ZGC is the modern industry standard for large-scale JVMs, as it decouples the pause time from the heap size.
Production Incident 30. You upgraded your JVM from an 8 gigabytes heap to a 32.5 gigabytes heap to handle more users. To your surprise, the application's memory usage spiked by 20% immediately, and you can now fit fewer objects in the 32 gigabytes heap than you could in a 30 gigabytes heap. What happened to the compressed oops?
Answer: this is the compressed oops threshold disaster. I would fix the memory efficiency by downsizing the heap. 1. Root cause. When the heap exceeds approximately 32 gigabytes, the exact limit depends on the JVM. The JVM can no longer use 32-bit compressed ordinary object pointers and switches to 64-bit pointers. This increases the size of every object reference by 4 bytes. 2. The paradox. Because every object is now 20% larger, the effective capacity of a 32.5 gigabytes heap is actually less than a 31 gigabytes heap. 3. Remediation. Downsize the heap to 31 gigabytes -XMX31G to re-enable compressed oops. This instantly reduces the memory footprint and increases object density. 4. Verification. Use Java-XX plus print flags final -version pipe grep. Use compressed oops to verify that the optimization is active. Pro tip: 32 gigabytes is the most dangerous heap size in Java. Always stay under 31 gigabytes or jump straight to 48 gigabytes plus. The no man's land between 32 gigabytes and 40 gigabytes is a waste of expensive RAM.
Production Incident 31. Following a migration from G1GC to ZGC to achieve sub-millisecond latency, your real-time bidding engine experienced massive 2-second spikes during peak traffic. JFR logs show allocation stalls, where application threads were forced to wait for the collector to catch up. How do you stabilize ZGC performance?
Answer: this is a ZGC allocation stall incident. ZGC is highly concurrent, but it is not magic. If you allocate faster than it can clean, it will block threads. I would resolve this by 1. Root cause analysis. The application's allocation rate, for example, 5 gigabytes per sec exceeded ZGC's reclamation capacity during a burst, causing the collector to enter a stall state to prevent 2. Immediate tuning. Increase the heap size -XMX to provide more headroom. ZGC performs better with larger heaps as it gives the concurrent cycles more time to complete before the heap hits 100%. 3. Concurrent thread tuning. Increase the number of GC threads using -XX GC threads to accelerate the reclamation phase, though this will consume more CPU from the application logic. 4. Code optimization. Profile the bid processing loop to identify object churn. Reducing the creation of temporary objects is the most effective way to prevent ZGC from stalling. Pro tip: ZGC is designed for latency-first apps, but it requires significantly more heap headroom than G1GC. A safe rule for ZGC is to ensure your live set occupies no more than 60% of the total allocated heap.
Production Incident 32. A transaction middleware JVM crashed after 6 months of continuous uptime. The SRE team discovers that GC log rotation was never enabled, and a single 80 gigabytes gc.log file filled the entire production disk, causing the OS to kill the process. How do you configure zero downtime logging?
Answer: this is a resource management failure. I would implement a robust GC log rotation strategy using the following JVM flags. 1. Immediate containment. Purge the massive log file and restart the service with updated flags. Verify that the production volume has at least 500 megabytes of free space reserved for system logs. 2. Configuration fix. Use the unified logging syntax -xlog introduced in Java 9+ to enforce file size limits and rotation counts. 3. Automation. Set file count equals 10 and file size equals 50 megabytes. This ensures that even if the app runs for years, the total log footprint will never exceed 500 megabytes. 4. Monitoring fix. Add a disk space alert to your infrastructure monitoring, for example, Datadog to trigger if the log volume exceeds 80% capacity. Pro tip: logging is an input or output operation. If your logs are on a slow disk or are not rotated, the JVM can actually block during GC cycles waiting for the disk to write the log entry. Always use rotation and point logs to high-speed storage. Here is JVM configuration showing how to implement unified logging with mandatory file rotation to prevent disk exhaustion. Disclaimer: always test code in a non-production environment. This code directs all garbage collection events to a specific file path, ensuring that performance data is not lost in standard out. Here is the code used to enforce rotation. It limits the system to 10 files of 50 megabytes each, capping the total disk usage for logs to exactly 500 megabytes regardless of uptime.
Production Incident 33. During a heavy processing batch, a full GC pause of 12 seconds triggered a Kubernetes readiness probe failure. Kubernetes automatically removed the pod from the load balancer, shifting 100% of the traffic to the remaining pods, which then also crashed due to the sudden load. How do you stop this cascading failure?
Answer: this is a health check failure where the infrastructure didn't account for JVM internal cycles. I would resolve this by 1. Immediate fix. Increase the failure threshold and period seconds in the Kubernetes YAML. A probe that checks every 1 second and fails after 3 attempts will kill a pod during a 5-second GC pause. 2. Tuning. Switch the JVM to G1GC and set -XX max GC pause millis equals 500 to keep individual pauses within the threshold of the readiness probe. 3. Infrastructure logic. Move from TCP probes to HTTP probes that point to a dedicated /health endpoint. If the JVM is in a full GC, the endpoint will not respond, but by increasing the timeout seconds, we can allow the pod to weather the storm rather than being evicted. 4. Root cause fix. Find the reason for the full GC likely incident 1 or 3 and fix the memory leak or allocation burst that triggered the 12-second pause. Pro tip: your Kubernetes liveness and readiness probes must be GC aware. If your max GC pause is 2 seconds, your probe timeout must be at least 3 seconds. Otherwise, your infrastructure will keep murdering healthy pods that are just busy cleaning memory.
Production Incident 34. Your message bus consumer is seeing 98% CPU utilization and 2-second GC pauses despite having 8 gigabytes of free heap. You find that the allocation rate is 2 gigabytes per second, but the reclamation rate is only 1.5 gigabytes per second. How do you resolve this thermodynamic performance imbalance?
Answer: this is an allocation rate saturation incident. Even if the heap is not full, the CPU cost of constantly cleaning object churn is overwhelming the app. I would immediately implement object pooling for frequently created objects like message buffers or JSON mappers to reduce the raw allocation pressure. By reusing objects instead of creating new ones, the allocation rate drops, allowing the GC to spend fewer CPU cycles and restoring the application's processing throughput. Pro tip: high CPU during GC is often caused by scavenging a massive young gen. If you allocate 2 gigabytes per sec, your CPU will spend all its time moving those objects around. Reduce the allocation rate first. Tuning the GC flags is only a secondary fix.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 35. A major bank suffered a 4-hour outage because heap occupancy alarms were repeatedly ignored by the night shift SREs. The dashboard showed a sawtooth pattern where the base-level memory usage was increasing by 50 megabytes every hour. How do you fix the alert fatigue and the underlying leak?
Answer: this is a strategic monitoring failure. The SREs ignored the alert because the heap looked fine after every minor GC. I would implement a trend-based alert that specifically monitors the heap usage after GC the live set. If this base level increases linearly for 3 consecutive hours, it is a guaranteed memory leak, regardless of total heap size. I would then use the automatic heap dump flag to capture a snapshot once the heap hits 80% occupancy to force the engineering team to diagnose the leak in the next sprint. Pro tip: never alert on current heap usage. It is too noisy. Always alert on the post-GC heap occupancy trend line. This is the only true indicator of a memory leak in a managed runtime.
Production Incident 36. A low-latency trading app is seeing jitter where 99.9% of requests are sub-millisecond, but 0.1% take 500 milliseconds. Analysis shows that Linux Transparent Huge Pages (THP) is causing the JVM to block during GC because the kernel is busy defragmenting memory pages in the background. How do you stabilize the OS JVM handshake?
Answer: this is a kernel JVM interaction failure. Linux THP is meant to help, but it often causes latency spikes for Java. I would handle this via 1. OS configuration. Disable transparent huge pages at the Linux kernel level by setting /sys/kernel/mm/transparent_hugeipage/ enabled to never. 2. JVM optimization. If you want the performance benefits of huge pages without the jitter, use static huge pages by pre-allocating them in the OS and using the -XX+, use large pages flag in the JVM. 3. Impact analysis. Use perf or ftrace to verify that the kernel CPU time drops during GC events after disabling THP. 4. Verification. Ensure that the JVM does not fall back to regular pages silently if huge pages are requested but not available. Pro tip: transparent huge pages is the hidden enemy of Java performance. Most Linux distributions have it enabled by default, but it is standard practice in high-performance JVM engineering to disable it or use explicit or static huge pages.
Production Incident 37. An e-commerce site using G1GC is seeing old gen usage creep up to 100% without triggering mixed collections. The logs show that G1 is ignoring regions that are 80% full of live data, eventually leading to a full GC. How do you make mixed collections more aggressive?
Answer: this is an ineffective mixed GC incident. G1GC was being too conservative with its cleanup. I would fix the tuning as follows. 1. Root cause. The default -XX G1 mixed GC live threshold % = 85 means G1 will only clean regions that have more than 15% garbage. If your data density is high, G1 will never clean those regions. 2. Tuning fix. Decrease -XX G1 mixed GC live threshold % to 60. This forces G1 to clean regions even if they are 60% full of live data, reclaiming the 40% garbage and stopping the old gen creep. 3. Cycle tuning. Increase -XX G1 mixed GC count target to 16 to spread the work over more cycles, preventing any single mixed collection from becoming too long and impacting latency. 4. Verification. Use a GC visualizer to ensure that the old generation usage line starts trending down after the threshold is lowered. Pro tip: G1GC is an economic collector. It will not clean a region if it thinks it is not worth the work. If your application stores many long-lived objects, you must lower the threshold to force the collector to work harder.
Production Incident 38. A log aggregator is crashing with because it keeps creating 100 megabytes log buffer byte arrays. Even with G1GC, the JVM is stalling because it cannot find enough contiguous regions for these humongous objects. How do you eliminate the allocation stalls?
Answer: this is a contiguous memory failure. I would re-architect the memory allocation strategy. 1. Root cause analysis. 100 megabytes arrays require 100 megabytes of perfectly adjacent RAM. If the heap is fragmented, the allocation will trigger a full GC to try and compact the space. 2. Immediate tuning. Increase the region size to 32 megabytes to reduce the number of objects classified as humongous. 3. Code fix. Refactor the code to use a composite buffer like Netty's composite byte buff or a list byte array where each byte array is exactly 1 megabytes. This allows the JVM to allocate the buffers in non-contiguous regions. 4. Alternative. Move the log buffers off heap using byte buffer.allocate direct, which completely bypasses the G1 region management. Pro tip: the larger the array, the faster the crash. In JVM engineering, you should never allocate arrays larger than 8 megabytes on the heap if you can avoid it. Use a collection of small buffers to keep the heap flexible. Here is Java code demonstrating how to replace a massive contiguous byte array with a segmented buffer approach to prevent heap fragmentation. Disclaimer: always test code in a non-production environment. This code attempts to allocate a single, massive, humongous object. If the G1 heap is even slightly fragmented, This will trigger an expensive full GC stall. Here is the code using smaller 1 megabyte segments. This allows the JVM to place each segment in any available heap region, eliminating the need for contiguous space and preventing allocation failures.
Production Incident 39. Your fraud detection app is experiencing 200 milliseconds latency spikes, but GC logs show pauses of only 10 milliseconds. You discover that JVM safepoints are taking 190 milliseconds to synchronize. Why are threads failing to reach the safe point quickly?
Answer: this is a SafePoint synchronization incident. A SafePoint requires all threads to stop, but some threads are refusing to check in. 1. Root cause. A thread is likely stuck in a counted loop, a simple for loop with an int counter. By default, the JIT compiler removes SafePoint checks from these loops for performance, meaning the loop must finish before the thread can stop for GC. 2. Immediate fix. Enable -XX plus use counted loop SafePoints. This forces the JIT to keep the checks inside the loops, ensuring threads stop immediately when requested. 3. Alternative fix. Change the loop counter from int to long. The JVM treats long counted loops as uncounted and automatically adds SafePoint checks. 4. Diagnosis. Use the flag -XX plus print SafePoint statistics to see which threads are holding up the synchronization. Pro tip: if your application pauses are longer than your GC pauses, you have a SafePoint problem. Check for long-running mathematical loops or heavy JNI calls that are not releasing the thread to the JVM quickly enough.
Production Incident 40. After reading a blog post, a developer added 12 complex GC tuning flags to the production auth service. Within 24 hours, the service crashed. How do you handle speculative tuning without baseline analysis?
Answer: this is a governance failure. I would immediately revert all GC flags to the platform default and re-establish a baseline. I would then implement a one flag at a time policy, where any tuning must be backed by a 48-hour O or B test in a staging environment using a workload that mimics production stress and idle periods. By using JFR Java Flight Recorder to prove a statistical improvement before moving to production, we eliminate the voodoo tuning that causes unstable environments. Pro tip: the modern JVM 17th November 2021 is incredibly smart at self-tuning. 90% of apps perform better with default settings. Never add a GC flag unless you have a graph proving exactly what problem it is solving.
Category 2 Conclusion. Mastering the metabolism of the JVM.
Garbage collection is not just a cleanup task, it is the metabolic heartbeat of your application. As we have seen in these 20 incidents, GC failures, from humongous object fragmentation to promotion loops, are rarely random. They are the logical result of how the JVM interacts with your code's allocation patterns and the OS memory subsystem. Mastery here means moving beyond default flags and learning to read the GC logs like a story. When you can balance throughput and latency, you ensure your platform can scale without the stop-the-world disasters that kill customer trust.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 2 to Category 3.
But even a perfectly clean heap cannot save an application if the CPU is trapped in an inefficient execution loop. If the heap is the metabolism, the CPU is the engine room that drives every transaction. When the CPU reaches 100% saturation, it is not always because your business is booming. It's often because your code is fighting itself. We now move from memory cleanup to CPU saturation, hotspots, and execution efficiency. Let's explore Category 3.
Category 3. CPU saturation incidents.
CPU saturation is the ultimate bottleneck. When the processors hit 100%, latency skyrockets, and the JVM loses its ability to handle even basic management tasks. In this category, we explore the invisible CPU killers. Catastrophic rejects backtracking, reflection-heavy serialization, and the silent overhead of excessive logging. We test your ability to use flame graphs and profilers to find the exact line of code that is turning your high-performance cores into expensive heaters.
Category 3. CPU saturation production incidents 41 to 60.
Here are the 20 scenarios covering execution hotspots and processor bottlenecks. Production incident 41. CPU reached 100% due to a recursive logging loop. Production incident 42. Rejects catastrophic backtracking consuming all available cores. Production incident 43. Excessive stack trace generation causing massive CPU spikes. Production incident 44. Reflection-heavy serialization reducing total platform throughput. Production incident 45. SSL handshake storms exhausting CPUs during a security rollout. Production incident 46. UUID generation becoming a hidden performance bottleneck. Production incident 47. JSON serialization pipeline saturating processors under high load. Production incident 48. Prometheus metric generation causing high CPU overhead. Production incident 49. Encryption overhead increasing node utilization beyond capacity. Production incident 50. Excessive logging appenders blocking processors and increasing latency. Production incident 51. Thread context switching exploding under extreme concurrency. Production incident 52. Kafka compression overhead increasing CPU consumption. Production incident 53. Spin locks wasting CPU cycles in high contention scenarios. Production incident 54. Dynamic proxy generation causing unexpected CPU spikes. Production incident 55. Flame graph revealing a hidden hotspot in a custom mapper utility. Production incident 56. JIT deoptimization storm suddenly increasing CPU utilization. Production incident 57. Bytecode instrumentation agents degrading overall performance. Production incident 58. XML transformation engine saturating CPUs during batch processing. Production incident 59. CPU throttling inside containers increasing response latency. Production incident 60. Monitoring agents consuming more CPU than the actual business logic. Total 20 incidents for CPU saturation. Let's dive into production incident 41.
Production incident 41. Within minutes of a new release, your customer support portal hit 100% CPU on all nodes. A quick JStack analysis shows thousands of threads stuck in the logging framework. You discover a recursive logging loop where an exceptions to string method calls the logger, which then re-triggers the exception. How do you stop the CPU meltdown?
Answer. This is a circular dependency failure in the diagnostic layer. I would immediately perform an emergency rollback of the deployment to stabilize the CPU and restore portal access. The fix involves refactoring the affected domain object to ensure its toString or message methods never perform any logic that could trigger an exception or invoke the logger. I would also implement a logging depth guard or use log4j's burst filter to drop logs if the same thread attempts to write more than 100 entries per second, providing a safety valve for future recursion bugs. Pro tip: never log an object inside its own toString method. This is a classic booby trap in Java engineering. Always log primitive fields or simple strings to avoid triggering the infinite loops that turn a simple error into a total cluster blackout. Here is Java code demonstrating a recursive logging loop that triggers an infinite CPU-intensive cycle. Disclaimer: always test code in a non-production environment. This code is the root cause. Because this is passed to the logger calls user.toString to format the message, which re-triggers the NPE and leads to infinite recursion.
Production Incident 42. A user profile service is experiencing massive latency spikes whenever a user enters a specific pattern in the bio field. CPU flame graphs show that 95% of thread time is spent in java.util.regex.pattern. How do you resolve this catastrophic backtracking disaster?
Answer: this is a regular expression complexity attack. I would resolve the CPU saturation using these steps. 1. Immediate action. Identify the problematic regex via the flame graph and replace it with a simple string dot contains or a fixed length validator to stop the CPU burn. 2. Root cause analysis. The regex likely used nested quantifiers, for example, a $+, which causes the engine's complexity to become exponential big O of 2 to the power of n when it fails to find a match. 3. Remediation. Refactor the regex to be possessive using ++ or atomic groups to prevent the engine from backtracking. This keeps the execution time linear big O of n. 4. Governance fix. Implement a regex execution timeout using a custom char sequence wrapper that checks for a time limit, ensuring no single regex can hold a CPU core for more than 100 milliseconds. Pro tip: regex is a program within a program. Never allow users to provide patterns, and never use nested quantifiers on unbounded input. Always test your regex against evil strings that are designed to fail slowly. Here is Java code demonstrating a vulnerable regex and the possessive quantifier fix to prevent catastrophic backtracking. Disclaimer: always test code in a non-production environment. Here is the code using the possessive quantifier. This tells the regex engine to never let go of matched characters, eliminating the backtracking that causes CPU saturation.
Production Incident 43. During an inventory sync batch job, the JVM CPU usage skyrocketed to 100%, but the logs showed very little activity. A thread dump revealed that the application was generating millions of business exceptions and calling e.getStackTrace on every one of them. How do you fix the stack walking bottleneck?
Answer: this is a diagnostic overhead failure. Generating a stack trace is an incredibly expensive CPU operation because the JVM must walk the entire thread stack and look up class and method metadata. I would first refactor the batch job to use control flow if else instead of exceptions for expected business logic like item not found. If exceptions are still needed, I would implement stackless exceptions by overriding the fill and stack trace method to return this immediately, which reduces the CPU cost of the exception to near zero. Pro tip: exceptions should be exceptional. If you are using them for normal logic, you are wasting 90% of your CPU on metadata lookups. A stackless exception is 100 times faster than a standard one. Here is Java code demonstrating a stackless exception to eliminate the CPU overhead of stack trace generation in high-frequency logic. Disclaimer: always test code in a non-production environment. This code overrides the default JVM behavior. By returning this without walking the stack, the exception becomes a simple object allocation, saving massive amounts of CPU.
Production Incident 44. A core banking gateway is hitting a performance wall at 2,000 transactions per second. Profiling shows that 30% of CPU time is spent in java.lang.reflect.method.invoke. It turns out a custom object mapper is using reflection to map every database field to a Java object. How do you optimize the mapping?
Answer: this is a reflection overhead saturation. I would resolve the bottleneck by moving from dynamic to compiled mapping. 1. Root cause. Reflection bypasses JIT optimizations and requires constant access checks by the JVM, making it significantly slower than direct method calls. 2. Short-term fix. Implement a reflective cache by storing method and field objects in a static map and calling setAccessible with true once to reduce access check overhead. 3. Long-term remediation. Migrate to a code generation mapper like map_struct. This generates plain Java code during the build phase, allowing the JIT compiler to inline the mapping logic for maximum CPU efficiency. 4. Advanced option. Use method handles or Lambda Metafactory to create call sites that the JVM can optimize nearly as well as direct bytecode. Pro tip: reflection is for frameworks, not for high-throughput pipelines. If a method is called millions of times per second, the 30% reflection tax will eventually force you to double your server count just to keep up. Here is Java code demonstrating how to use method handles to achieve near-native performance compared to standard reflection. Disclaimer: always test code in a non-production environment. This code looks up the method handle once. Unlike reflection, method handles can be constant folded by the JIT, making subsequent calls significantly faster.
Production Incident 45. After enabling strict TLS 1.3 across the cluster, your CPU utilization increased by 25%, and the login service crashed during the morning rush. Metrics show an SSL handshake storm where thousands of mobile clients are performing full handshakes every minute. How do you optimize the security overhead?
Answer: this is a cryptographic handshake saturation. Every new TLS connection requires a complex RSA or ECC handshake that is extremely CPU intensive. I would immediately enable TLS session resumption using session tickets to allow returning clients to skip the heavy crypto math. Furthermore, I would move the SSL termination from the Java JVM to a specialized edge proxy or load balancer like Nginx or AWS ALB that uses hardware-accelerated chips for encryption, freeing the JVM to focus entirely on business logic. Pro tip: never terminate SSL inside the JVM for high-traffic apps. Java's JSSC is robust, but it cannot compete with the C-based implementation of Nginx or specialized hardware. Offload the crypto tax to the infrastructure layer.
Production Incident 46. A distributed logger service is hitting a CPU ceiling. Flame graphs reveal that java.util.uuid.random UUID is responsible for 15% of total CPU time. The service generates an ID for every log line, and the secure random source is causing thread contention. How do you optimize ID generation?
Answer: this is a secure random contention incident. I would switch to a more efficient ID strategy. 1. Root cause. UUID.random UUID uses secure random, which is synchronized and can block threads while waiting for entropy from the OS. This causes massive CPU spinning under high concurrency. 2. Remediation. If cryptographic security is not required, for example, for log tracing, switch to a snowflake ID or a long adder-based counter, which are designed for high concurrency without synchronization. 3. Tuning fix. If UUIDs are mandatory, use a thread local random source or pre-generate batches of UUIDs to reduce the frequency of the synchronized entropy calls. 4. Verification. Monitor the block time in your profiler. If it drops after the change, you have successfully removed the synchronization bottleneck. Pro tip: UUID.random UUID is for security. It is not for high-speed identification. For tracing or internal IDs, use a simple atomic long or a custom UUID implementation that uses thread local random for a 10 times CPU speedup. Here is Java code demonstrating the use of thread local random for high-performance ID generation compared to synchronized secure random. Disclaimer: always test code in a non-production environment. This code uses the thread local source, which eliminates the lock contention found in the standard UUID.random UUID call, drastically reducing CPU usage under heavy load.
Production Incident 47. A product search API is hitting 100% CPU during peak hours. Profiling reveals that Jackson JSON serialization is the primary consumer of CPU cycles. The application is returning massive 10 megabytes JSON responses for every search query. How do you reduce the serialization tax?
Answer: this is a payload density saturation. Serialization is a CPU-bound task. The more data you serialize, the more CPU you burn. I would first implement field filtering using @JSONView or GraphQL to ensure only the required 5 fields are returned instead of the full 200 field product object. I would then enable gzip compression at the load balancer level to reduce the network payload, and consider switching to a binary format like protobuf or avro for internal microservice communication, which are 5 times to 10 times more CPU efficient than JSON. Pro tip: the best way to optimize serialization is to serialize less data. If your JSON is 10 megabytes, no library in the world will save your CPU. Minimize the response size at the API contract level first.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 48. Following a migration to Prometheus for monitoring, your JVM CPU baseline increased by 15%. You discover that scraping the /metrics endpoint takes 4 seconds and consumes 100% of a CPU core every time. How do you optimize observability overhead?
Answer: this is a metric cardinality failure. The CPU spike occurs because Prometheus is iterating through hundreds of thousands of time series in memory to generate the text response. I would immediately audit the metrics and remove any high cardinality tags like user_ID or order_ID from the counters. I would also increase the scrape interval from 10 seconds to 60 seconds to reduce the frequency of the CPU-intensive scrape and ensure the Prometheus client is using a buffered or cached response rather than recalculating the entire registry on every request. Pro tip: Prometheus metrics are for aggregates, not transactions. If your metrics endpoint takes more than 100 milliseconds to respond, you are leaking data into your metrics that belongs in your logs. Keep your metric count under 5,000 for a healthy JVM.
Production Incident 49. After implementing field-level encryption AES 256 for a PII-heavy database, the user profile service CPU utilization jumped from 40% to 95%. Transactions that took 10 milliseconds are now taking 80 milliseconds. How do you mitigate the encryption tax?
Answer: this is a cryptographic throughput bottleneck. AES encryption is highly CPU-intensive when performed in software. I would first verify that the JVM is using AES-NI hardware acceleration by checking the -XX+ use AES and -XX+ use AES intrinsics flags. If it is already enabled, I would implement batch encryption to reduce the number of JNI calls to the crypto provider, or use envelope encryption, where only a small data key is encrypted or decrypted frequently, while the actual PII data is cached in an encrypted at rest session to minimize the total number of crypto operations. Pro tip: AES is fast on modern CPUs, but the context switch between Java and the native crypto library can be slow. Use AES-NI and always benchmark your crypto provider bouncy castle versus OpenJDK to find the most efficient implementation for your specific hardware.
Production Incident 50. A payment reconciliation job is taking 8 hours to finish instead of 2. Profiling shows that threads are frequently blocked in wait states. You find that the application is using 5 different logging appenders: console, file, logstash, Datadog, and Slack, and all are configured to be synchronous. How do you unblock the processors?
Answer: this is an I/O blocking CPU incident. Because the appenders are synchronous, every log.info call forces the business thread to stop and wait for the network or disk write to finish. I would immediately wrap all appenders in an async appender in logback or log4j2 with a large internal buffer and a discarding threshold to drop non-critical logs if the buffer fills up. This decouples the business logic from the I/O latency, allowing the CPU to process transactions at full speed while a background thread handles the logging telemetry. Pro tip: synchronous logging is the performance killer of enterprise Java. Always use asynchronous appenders in production. Your business threads should never, ever wait for a log message to be written to a disk or sent over a network.
Production Incident 51. A legacy monolith migration to a high concurrency microservice environment resulted in a total CPU collapse. While CPU was at 100%, actual application throughput was 0. Profiling shows that context switching is consuming 70% of processor time. How do you rebalance the thread orchestration?
Answer: this is a thread saturation incident. The OS is spending more time swapping threads in and out of the CPU cores than actually executing Java bytecode. I would resolve this as follows. 1. Root cause analysis. The application was configured with a fixed thread pool of 2,000 threads on a node with only 8 CPU cores, leading to massive kernel-level scheduling overhead. 2. Immediate remediation. Downsize the thread pools to match the core count times 2 rule of thumb. This reduces the contention for CPU time slices and allows the OS to maintain thread affinity. 3. Architectural fix. Migrate the I/O-bound tasks to virtual threads Java 21+. Virtual threads are managed by the JVM, not the OS, allowing you to run millions of tasks without the heavy cost of kernel context switching. 4. Monitoring. Monitor the system.cpu.context_switches metric. If it exceeds 50,000 per second, your thread count is too high for your hardware. Pro tip: more threads does not mean more speed. Beyond a certain point, adding threads actually slows down your application. For CPU-bound tasks, your pool size should never exceed the number of available cores.
Production Incident 52. After enabling gzip compression on your Kafka producer to save network bandwidth, the producer nodes hit 100% CPU, causing a massive backlog in the upstream order pipeline. How do you optimize the compression strategy?
Answer: this is a compression tax saturation. Gzip is highly CPU-intensive and often becomes a bottleneck in high-throughput producers. I would immediately switch the compression codec from gzip to LZ4 or Snappy. These codecs are specifically designed for high-performance streaming. They offer slightly lower compression ratios but are 5 times to 10 times faster on the CPU, effectively unblocking the producer and restoring the system's overall throughput. Pro tip: compression is a trade-off between CPU and network. In 10 Gbps modern data centers, the CPU is usually the more expensive resource. Always prefer LZ4 for Kafka producers. It is the industry standard for high-speed Java messaging.
Production Incident 53. An ultra-low latency order matching engine is pinning a CPU core at 100% even during periods of zero traffic. You discover a custom spin lock used to avoid thread parking latency is wasting millions of CPU cycles while waiting for orders. How do you optimize the wait strategy?
Answer: this is a busy waiting inefficiency. While spin locks reduce latency, they destroy CPU efficiency. I would implement the following mechanical sympathy fix. 1. Code fix. Implement a phased wait strategy. Instead of a tight while with true loop, use the thread dot on spin wait hint introduced in Java 9. This tells the CPU that the thread is in a spin loop, allowing the processor to optimize power and resource usage. 2. Back-off strategy. If the spin lock exceeds 1,000 iterations, transition to a thread yield or a short lock support park nano-s with one to free the core for other system tasks. 3. Hardware optimization. Use CPU affinity via taskset or ISOCPIS to ensure the matching engine has exclusive access to the core, preventing other threads from interrupting the spin loop. Pro tip: thread on spin wait is a game changer for low-latency Java. It emits a pause instruction at the assembly level, which prevents the CPU pipeline from flushing, reducing both power consumption and latency when the lock is finally released. Here is Java code demonstrating the use of thread on spin wait to optimize busy waiting loops in low-latency matchers. Disclaimer: always test code in a non-production environment. This code invokes a specialized JVM intrinsic. It signals to the hardware that this thread is in a spin loop, allowing the CPU to reduce its internal clock cycles and save power while maintaining the lowest possible wake-up latency.
Production Incident 54. A dynamic routing service is experiencing periodic CPU spikes and metaspace errors. You discover that a custom library is generating a new cglib dynamic proxy for every single incoming request to handle cross-cutting concerns. How do you resolve the proxy overhead?
Answer: this is a runtime code generation failure. Creating a dynamic proxy involves generating new bytecode, which is a heavy CPU task, and then loading it into the metaspace, which is never reclaimed if the class loader persists. I would refactor the service to cache the generated proxy classes based on the target class type. By reusing the proxy class and only creating new instances, we eliminate the CPU-heavy bytecode generation and the metaspace leak simultaneously. Pro tip: dynamic proxies JDK or cglib should be created once during application startup. If you are generating classes at request time, you have a fundamental architectural flaw that will eventually crash your JVM.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 55. A data transformation gateway is hitting a CPU wall at 500 records per second. An async profiler flame graph reveals that a massive 40% of CPU time is spent inside Apache Commons bean utils.copy properties. How do you eliminate this hidden hotspot?
Answer: this is a reflection-heavy utility bottleneck. Bean utils uses intensive reflection to inspect getters and setters on every call. I would resolve the bottleneck as follows. 1. Immediate fix. Replace the generic copy properties call with manual getters and setters for the most frequent data paths. This allows the JIT compiler to inline the code perfectly. 2. Architectural remediation. Migrate to map struct or Selma. These libraries generate the mapping code during the build phase compile time, resulting in zero reflection at runtime and near-native CPU performance. 3. Alternative. Use Lambda Factory to create high-speed accessors if the field names are only known at runtime. This is significantly faster than standard method .invoke. Pro tip. Apache Beanutils is notoriously slow for high-throughput applications. In modern days, there is no excuse for using reflection-based mapping. MapStruct is the industry standard for CPU-efficient Java object transformations. Here is Java code demonstrating the transition from reflective Beanutils to a compiled MapStruct interface for CPU-efficient object mapping. Disclaimer: always test code in a non-production environment. This code defines the mapping contract. MapStruct generates the actual implementation at compile time using standard getters and setters, which the JIT can optimize far better than reflection-based property copying.
Production Incident 56. A risk assessment engine experienced a sudden 50% drop in throughput after 3 hours of steady performance. Monitoring shows a JIT deoptimization storm. It appears that a specific profile pollution issue occurred where a method that was previously monomorphic suddenly received multiple different implementation types. How do you stabilize the JIT compiler?
Answer: this is a polymorphic inlining failure. The JIT compiler optimized the code assuming only one implementation existed monomorphic. When a second type appeared, the JIT deoptimized the code, reverting to interpreted mode before recompiling it as megamorphic, which is much slower. I would refactor the critical path to use interface-based logic that avoids mixing too many types in the same call site, or use the -XX max inline level flag to allow deeper inlining. Most importantly, I would use the -XX plus print compilation flag to identify which methods are frequently deoptimizing and refactor them to be simpler and more predictable for the compiler. Pro tip: JIT compilers love sameness. If you pass 10 different implementations of an interface to the same method, you will pollute the profile and kill performance. Try to keep your high-frequency call sites monomorphic or bimorphic.
Production Incident 57. After installing a new APM monitoring agent, your JVM CPU baseline jumped by 20%. The flame graph shows significant time spent in bytecode instrumentation and advice code added by the agent. How do you reduce the observer effect?
Answer: this is an instrumentation overhead incident. The agent is rewriting too many methods. I would optimize the agent configuration as follows. 1. Refinement. Use the agent's exclude list to prevent it from instrumenting high-frequency, low-latency methods like simple getters or setters or utility methods. 2. Sampling adjustment. Change the agent from tracing every call to sampling every 10th or 100th call. This drastically reduces the CPU cycle spent on telemetry. 3. Agent upgrade. Ensure the agent is using the latest invoke dynamic-based instrumentation, which is significantly more efficient than older redefined class methods. 4. Off-process analysis. Move heavy processing of captured spans to an out-of-process collector like an open telemetry collector to ensure the JVM is not spending CPU cycles on serializing its own traces. Pro tip: an APM agent should never consume more than 3 to 5% of your CPU. If it is hitting 20%, it is poisoning your performance metrics. Exclude your hot loops from instrumentation immediately.
Production Incident 58. Your B2B integration engine is saturating all 32 CPU cores while processing XML-based invoices. Profiling reveals that the XSLT transformer is reparsing the stylus sheet for every single invoice. How do you optimize the transformation efficiency?
Answer: this is a redundant parsing bottleneck. XML or XSLT processing is extremely CPU intensive. I would immediately implement template caching. Instead of creating a new transformer from the source XML for every request, I would create a templates object once during startup. The templates object is a thread-safe, pre-compiled representation of the XSLT. By reusing this compiled template to create transformer instances, we skip the expensive parsing and validation phases, reducing CPU usage by over 80%. Pro tip: in Java XML processing, transformers are disposable, but templates are permanent. Always pre-compile your XSLT into a templates object and cache it to avoid turning your CPU into an XML parser. Here is Java code demonstrating the use of a pre-compiled templates object to optimize XSLT transformation performance. Disclaimer: always test code in a non-production environment. This code performs the heavy lifting of parsing the XSLT and compiling it into an optimized internal format. This is done only once, saving massive CPU cycles on subsequent transformations.
Production Incident 59. A Kubernetes-hosted Java service is experiencing latency jitter where the P99 response time spikes to 500 milliseconds, even though the JVM CPU usage is reported as only 30%. You discover that the CFS throttling metric is high in Prometheus. How do you resolve the container throttling?
Answer: this is a CFS quota mismatch. The JVM is being punished by the Linux kernel for using its CPU allotment too quickly within a single 100 milliseconds window. I would fix this as follows. 1. Analysis. Check the /sys/fs/cgroup/cpu/cpu.stat file for nr_throttled. If this is increasing, Kubernetes is hard killing your CPU cycles for the remainder of the period. 2. Remediation. Increase the CPU limit in the Kubernetes pod spec. If you have 2.0 cores requested but 4.0 cores used in bursts, the CFS quota will throttle you even if the total node CPU is low. 3. JVM alignment. Ensure -XX active processor count is set correctly. If the JVM thinks it has 16 cores but the container limit is 2.0, it will spawn too many threads, leading to bursting that triggers throttling. 4. Advanced. Disable CPU limits entirely using only requests if your cluster allows it, moving to a shared core model to eliminate the 100 milliseconds quota logic. Pro tip: CPU throttling is the #1 cause of unexplained Java latency in Kubernetes. The kernel does not care if your JVM is idle. It only cares if you exceeded your 100 millisecond slice. Always set your limits high enough to handle your GC bursts.
Production Incident 60. A monitoring agent intended to find performance issues actually caused a production outage. The agent was configured to capture full thread dumps every 5 seconds. The resulting SafePoint pauses and JSON serialization of 2,000 thread stacks drove the CPU to 100%. How do you design safe observability?
Answer: this is an observer-induced crash. I would immediately disable the aggressive thread dumping. To build a safer system, I would move toward event-driven diagnostics using JDK Flight Recorder JFR. JFR is built into the JVM kernel and can capture thread states and stack traces with less than 1% CPU overhead. I would configure JFR to continuous mode and only dump the recording to disk when a specific threshold like 90% CPU is hit, ensuring we have the diagnostic data we need without killing the patient we are trying to monitor. Pro tip: manual JStack calls or thread dumps are expensive because they force a global SafePoint. For production monitoring, use JFR or Async Profiler. They are designed for zero-impact observability.
Category 3 Conclusion. Optimizing the engine room.
CPU saturation is the ultimate indicator of architectural inefficiency. As we have seen in these 20 incidents, the 100% CPU wall is rarely hit because of valid business logic. It is hit because of rejects backtracking, reflection tax, or the silent overhead of observability tools. Mastering CPU performance means moving beyond high-level code and understanding how the JIT compiler, the OS scheduler, and your algorithms interact with the hardware. When you eliminate the hidden hotspots, you do not just save money on cloud bills, you unlock the true throughput potential of the JVM.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 3 to Category 4.
But even the most CPU-efficient code cannot save a platform if the threads responsible for executing that code are stuck waiting for each other. If the CPU is the engine, then threading is the transmission that transfers power to the road. When your transmission locks up, through deadlocks, starvation, or pool exhaustion, the engine revs to no effect. We now move from the raw execution of a single core to the complex orchestration of the entire multi-threaded ecosystem. Threading and concurrency incidents. Let's explore Category 4.
Category 4. Threading and concurrency incidents.
Concurrency is where Java's greatest strength meets its most dangerous failures. In this category, we move into the world of shared memory and contested resources. We will analyze deadlocks that freeze transaction pipelines, thread pool exhaustion that blocks global API gateways, and the subtle starvation that occurs when unfair locks favor the wrong threads. We test your ability to read thread dumps like a crime scene, to find the locked monitor that brought down the enterprise.
Category 4. Threading and concurrency production incidents 61 to 80.
Here are the 20 scenarios covering pool exhaustion and synchronization failures. Production incident 61. Thread pool exhaustion blocking all incoming API requests. Production incident 62. Deadlock between the audit service and the transaction service. Production incident 63. Global platform freeze on a synchronized cache refresh loop. Production incident 64. Kafka consumers stop polling due to blocked processing threads. Production incident 65. Database connection pool starvation freezing request handling. Production incident 66. Async executor queues growing infinitely and exhausting heap. Production incident 67. Servlet container threads exhausted during a downstream API slowdown. Production incident 68. Netty event loops blocked by accidental synchronous code calls. Production incident 69. Priority thread starvation causing high-value API timeouts. Production incident 70. Scheduled tasks overlapping and exhausting the executor threads. Production incident 71. Thread dumps showing 4,000 waiting threads during peak load. Production incident 72. Unfair lock acquisition causing long-tail request starvation. Production incident 73. Lock convoy effects drastically reducing system throughput. Production incident 74. Distributed locks failing to release ownership of stale records. Production incident 75. Locking I/O inside a reactive pipeline freezing the event loops. Production incident 76. Thread local contamination leaking secure request contexts. Production incident 77. Native thread exhaustion leading to 20,000 unmanaged threads. Production incident 78. Completable future deadlock blocking asynchronous business flows. Production incident 79. Unsafe singleton initialization causing state corruption in production. Production incident 80. Reentrant lock misuse causing intermittent application hangs. Total 20 incidents for threading and concurrency. Let's start with production incident 61.
Production incident 61. Your primary payment ingester stopped responding to all health checks. A thread dump reveals that 100% of the HTTP worker threads are in a waiting state, blocked on an internal thread pool that has reached its maximum limit. What is your containment and remediation strategy?
Answer: this is a nested pool deadlock or exhaustion incident. I would handle this via the following architectural steps. 1. Immediate containment. Restart the service with an increased HTTP thread limit to restore connectivity, but implement request shedding at the load balancer to prevent the pool from immediately resaturating. 2. Root cause analysis. Analyze the dump to see if pool A is waiting for a result from pool B. If both pools are full and mutually dependent, you have a distributed deadlock. 3. Remediation. Implement caller runs policy or sized queues for the internal pool. This ensures that when the pool is full, the calling thread processes the task itself, providing natural backpressure to the HTTP layer. 4. Monitoring. Add a micrometer gauge to monitor the executor.active versus executor.max threads. Trigger a PagerDuty alert if any pool stays at 95% capacity for more than 60 seconds. Pro tip: never use a fixed thread pool without a sized queue for high-throughput apps. An unbounded queue will hide the bottleneck until the JVM crashes with an while a fixed pool without a queue will cause immediate thread starvation.
Production Incident 62. A critical financial close process is stuck. Thread dumps show a classic deadlock where thread audit service holds lock 1 and is waiting for lock 2, while thread B transaction service holds lock 2 and is waiting for lock 1. How do you break the deadlock and prevent it from returning?
Answer: this is a lock ordering failure. I would immediately use JCMD PID thread.print to identify the specific thread IDs and memory addresses involved, then manually kill one of the threads or restart the node to clear the contention. The permanent fix is to enforce a strict lock ordering across the entire application. Every service must acquire lock 1 before lock 2. Additionally, I would replace standard synchronized blocks with reentrant lock.try lock with a 5-second timeout, ensuring that if a deadlock starts to form, the thread will eventually give up and throw an error rather than freezing the JVM forever. Pro tip: deadlocks are caused by circular wait. The best way to prevent them is to avoid nested locks entirely. If you must use multiple locks, always acquire them in alphabetical or numerical order, according to a documented global standard.
Production Incident 63. Your product catalog service experiences a total freeze every time the cache is refreshed. Analysis shows that the refresh thread is holding a global synchronized lock on the cache, blocking 200 reader threads from accessing the data for 30 seconds. How do you optimize the synchronization?
Answer: this is a write starvation and coarse-grained locking incident. I would migrate to a more granular concurrency model. 1. Root cause. The synchronized keyword is exclusive. It prevents multiple readers from accessing the cache even if no data is currently being changed. 2. Immediate fix. Replace the synchronized block with a reentrant read-write lock. This allows 1,000 threads to read simultaneously, only blocking when the writer thread needs to update the data. 3. Optimization. Move to a concurrent collection like concurrent hash map combined with a loading cache pattern. This uses compare and swap CAS operations to eliminate locks for readers entirely. 4. Verification. Compare the average wait time metric before and after. Readers should see 0 wait time during a refresh in the optimized version. Pro tip: synchronized blocks are the hammer of concurrency. They work, but they are heavy and slow. For caches, always use read-write locks or concurrent collections to allow parallel reading while writing is in progress. Here is Java code demonstrating the shift from exclusive synchronized blocks to a reentrant read-write lock to allow high concurrency reading during cache updates. Disclaimer: always test code in a non-production environment. This code acquires the shared read lock. It allows an unlimited number of threads to access the cache simultaneously, provided no thread is currently holding the right lock. Here is the code where the writer thread requests exclusive access. It will wait for all active readers to finish, but once held, it prevents any new readers from entering until the update is complete.
Production Incident 64. A Kafka consumer cluster stopped processing messages, but the pods remained running. Thread dumps show that the consumer polling thread is blocked indefinitely because a processing thread is stuck in a database call that has no timeout. How do you unblock the messaging pipeline?
Answer: this is a poll loop starvation incident. In Kafka, if the processing logic blocks the main poll thread, the consumer fails to send heartbeats, triggering a rebalance storm that can crash the entire consumer group. I would immediately implement a decoupled architecture by handing off the Kafka message to an internal executor service for processing, allowing the main thread to return to the poll loop instantly. I would also enforce mandatory socket timeouts on the database driver to ensure that a slow query cannot pin a processing thread indefinitely. Pro tip: the Kafka poll thread is sacred. It should only be used to fetch data and commit offsets. Never perform I/O or heavy computation inside the poll loop. Hand that work off to a dedicated worker pool to keep the consumer group stable.
Production Incident 65. Your order entry API is returning 503 service unavailable. Metrics show that all 100 Hikari CP database connections are active, but the database CPU is only at 5%. Thread dumps show all Java threads are blocked waiting for a connection from the pool. How do you resolve the pool starvation?
Answer: this is a connection leak or long-running transaction incident. I would resolve the starvation as follows. 1. Diagnosis. Enable leak detection threshold in Hikari CP. If a thread holds a connection longer than 30 seconds without returning it, the pool will log a stack trace of the culprit. 2. Root cause analysis. Check if threads are performing external REST calls while still holding the database connection. This holds the connection idle, starving other threads of the resource. 3. Remediation. Refactor the code to fetch data to release connection to call REST API. Never hold a database lock or connection during a network call to an external service. 4. Tuning. Increase the connection timeout to 5 seconds to allow for temporary bursts, but do not just make the pool bigger. That usually just shifts the bottleneck to the database disk I/O. Pro tip: connection pool starvation is often a logic error, not a capacity error. If your threads are performing external I/O while holding a DB connection, you are wasting the most expensive resource in your stack. Close your connections early.
Production Incident 66. An event analytics app is crashing with out-of-memory error. Java heap space. You find that the linked blocking queue used by your add-async executor has grown to 5 million pending tasks. How do you re-architect the async pipeline?
Answer: this is an unbounded queue failure. I would implement a size strategy with proper backpressure. 1. Root cause. The default Spring add-async or executors.new fixed thread pool uses an unbounded queue. If tasks arrive faster than they are processed, the queue consumes the entire heap. 2. Remediation. Replace the linked blocking queue with an array blocking queue of a fixed size, for example, 5,000. 3. Backpressure fix. Configure a rejected execution handler. Use the caller runs policy to slow down the producer thread, forcing it to execute the task itself when the queue is full. 4. Monitoring. Add a gauge for executor.queue remaining capacity. If it hits 0, your system is officially backpressured and needs to scale out. Pro tip: unbounded is the most dangerous word in concurrency. Every queue in a production JVM must have a limit. If you do not limit the queue, the JVM will limit your uptime by crashing. Here is Java code demonstrating how to configure a thread pool executor with a fixed size queue and a backpressure policy. Disclaimer: always test code in a non-production environment. This code defines the hard limit. By using a bounded array blocking queue, we ensure that the memory footprint of the task backlog is capped, preventing crashes during traffic surges. Here is the code implementing backpressure. When the queue is full, the thread that submitted the task is forced to run it, naturally slowing down the ingestion rate.
Production Incident 67. During a slow response from a third-party credit score API, your entire loan application portal went offline. You find that all 200 Tomcat servlet threads are blocked waiting for the third-party response, leaving no threads to serve the login or homepage requests. How do you isolate the failure?
Answer: this is a thread isolation failure. The credit API took down the entire portal because they shared the same global thread pool. I would immediately implement the bulkhead pattern using a library like Resilience4j. By assigning the credit API its own dedicated small thread pool, for example, 20 threads, I ensure that even if that API hangs, it can only consume 20 threads, leaving the other 180 Tomcat threads free to serve the rest of the application. I would also implement a circuit breaker to stop calling the slow API entirely if the failure rate exceeds 50%. Pro tip: never let a slow downstream kill your upstream. Always use bulkheads to isolate different integration points into their own thread pools. One slow service should never be able to monopolize your entire container's thread count.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 68. You migrated to a reactive architecture using Project Reactor and Netty to save threads. However, your API latency actually increased, and the system is freezing. You discover that a developer added a log.info to a database via a synchronous JDBC driver inside a flat map. Why did this crash the reactive engine?
Answer: this is an event loop starvation incident. Reactive engines like Netty use a very small number of threads, usually matching the CPU core count. If you perform a blocking call like synchronous JDBC on one of these threads, you freeze that event loop, which might be responsible for 10% of all active user connections. I would immediately wrap the blocking JDBC call in a publish on with schedulers bounded elastic block. This moves the blocking work to a dedicated thread pool designed for I/O, allowing the Netty event loops to stay non-blocking and responsive. Pro tip: the golden rule of reactive Java: never block the event loop. Even a single thread .sleep or a synchronous logger call can paralyze your entire high-performance reactive pipeline.
Production Incident 69. Your VIP dashboard is experiencing high latency, while standard users are seeing fast responses. You find that your VIP priority pool is being starved of CPU time because the standard pool has 500 threads fighting for the same CPU cores. How do you enforce thread priority?
Answer: this is a resource starvation incident. Standard OS-level thread priorities often fail in high-load Java apps. I would resolve this by 1. Architectural shift. Move from priority to quotas. Downsize the standard pool to a smaller number of threads so it cannot saturate the OS scheduler. 2. CPU affinity. If running on bare metal or specialized VMs, use CPU pinning to give the VIP pool its own dedicated CPU cores that the standard pool cannot touch. 3. Traffic shaping. Implement rate limiting at the load balancer level for non-VIP traffic, ensuring the JVM always has headroom to process the high-value requests immediately. 4. JVM hinting. Use thread.set priority with thread.max_priority for VIP workers, but verify with top-h if the OS is actually honoring these hints. Pro tip: thread priority is a suggestion, not a command. The OS scheduler can and will ignore you. The only guaranteed way to give VIP requests more power is to strictly limit the resources available to standard requests.
Production Incident 70. A scheduled batch that runs every 5 minutes started overlapping, causing a thread leak that eventually crashed the JVM. You find that each task takes 6 minutes to finish, and the scheduled executor service is spawning new threads to handle the backlog. How do you stabilize the schedule?
Answer: this is a schedule overrun failure. I would change the execution strategy to prevent concurrency. 1. Code change. Switch from schedule at fixed rate to schedule with fixed delay. This ensures the 5-minute timer only starts after the previous task has finished, preventing any possibility of overlapping. 2. Concurrency guard. Implement a locking mechanism like a try-lock or a distributed Redis lock at the start of the task. If a task is already running, the new instance should immediately exit. 3. Monitoring. Add an alert for task execution duration. If a 5-minute task starts taking 6 minutes, the SRE team needs to be notified of the performance regression before the backlog becomes terminal. Pro tip: fixed rate is for clocks, fixed delay is for work. If your task performs I/O, never use schedule at fixed rate. You are one network slowdown away from a cascading thread explosion. Here is Java code demonstrating the shift from fixed rate scheduling to fixed delay to prevent task overlap and thread exhaustion. Disclaimer: always test code in a non-production environment. This code ensures a 5-minute gap between executions. Even if the task takes 10 minutes, the next one will not start until 5 minutes after the first one finishes, guaranteeing zero overlap.
Production Incident 71. During a peak hour traffic surge, your social feed microservice hit a CPU ceiling. A thread dump revealed 4,000 threads in a waiting or timed_waiting state, mostly associated with unmanaged ad hoc thread pools created inside a request-scoped bean. How do you stabilize the thread count?
Answer: this is a thread leaking pool incident. The application was creating a new executor service for every request instead of using a shared singleton. I would resolve this as follows. 1. Immediate action. Perform an emergency restart to clear the 4,000 OS-level threads and instantly implement a max thread limit at the container level to prevent the JVM from bringing down the entire node. 2. Root cause analysis. Use a profiler to find the allocation site of new thread pool executor. Any thread pool not defined as a static final constant or a Spring singleton is a major architectural red flag. 3. Remediation. Refactor the logic to use a centralized managed thread pool task executor. This ensures that threads are reused across requests and the total thread count never exceeds a predefined safety limit, for example, 200. 4. Monitoring. Implement an alert on the JVM.threads.live metric. If the thread count grows linearly with the request rate, you have a leak in your thread lifecycle management. Pro tip: every Java thread costs roughly 1 MB of native memory for its stack. 4,000 threads is not just a CPU problem. It's a 4 GB native memory tax that will eventually trigger an unable to create native thread crash.
Production Incident 72. A high-value trade processing engine is seeing long-tail latency where 1% of transactions take 10 seconds, while others take 5 milliseconds. You discover that the application is using unfair reentrant locks, allowing new threads to jump the queue and starve older threads of the lock. How do you enforce fairness?
Answer: this is a thread starvation incident caused by the default unfair setting of Java locks, which prioritizes throughput over order. I would immediately switch the critical lock to fair mode by passing true to the reentrant lock constructor. While this slightly reduces total system throughput due to increased context switching, it guarantees that threads are served in a first-in first-out FIFO order, eliminating the 10-second latency spikes. For an even more scalable fix, I would evaluate moving to a lock-free data structure using atomic reference or long adder to avoid the queuing problem entirely. Pro tip: fairness in locks is expensive but necessary for predictable SLAs. If your P99 latency is significantly higher than your P50, check if an unfair lock is allowing barging threads to repeatedly steal the core from waiting threads.
Production Incident 73. A user session service is suffering from a lock convoy effect. Every time a high-frequency synchronized method is called, hundreds of threads arrive at the lock simultaneously, causing the OS to spend all its time moving threads from running to waiting states. How do you break the convoy?
Answer: this is a high-contention synchronization failure. I would implement lock splitting and stripping techniques to reduce the bottleneck. 1. Lock splitting. Instead of one global lock for the entire session manager, split the logic into multiple smaller locks, one for read-only profile data and one for write-heavy session state. 2. Lock stripping. Use the concurrent hash map approach where you have an array of lock stripes. Threads only compete for a lock if they are accessing the same bucket, reducing contention by a factor of 16 or 32. 3. Code fix. Replace the synchronized keyword with long adder for simple counters. Long adder uses an internal array of variables to avoid contention, making it significantly faster than a single synchronized counter. 4. Verification. Use JStack to monitor the number of threads in blocked state. If the number drops significantly, you have successfully broken the convoy. Pro tip: a lock convoy occurs when the overhead of managing the lock is higher than the work done inside the lock. If your synchronized block is only 2 lines of code, you are almost always better off using an atomic variable or a striped lock.
Production Incident 74. Your inventory reservation system uses distributed locks via RIDIs. During a network flicker, the Java client failed to release a lock on a high-demand SKU, and because the lock had no TTL time to live, the item remained locked for 24 hours, preventing all sales. How do you re-architect safe distributed locking?
Answer: this is a leaked ownership incident in a distributed environment. I would immediately implement a lease pattern by always providing a TTL when acquiring the lock, ensuring that if the Java process crashes or loses network, the lock automatically expires in RIDIs after 30 seconds. To prevent the lock from expiring while the task is still running, I would use the redisen watchdog pattern, which periodically extends the lease as long as the Java thread is still alive and healthy. Finally, I would wrap the lock acquisition in a try with resources style block to ensure the unlock command is sent even if a runtime exception occurs. Pro tip: a distributed lock without a TTL is a production time bomb. Always assume your Java process will be killed -9D at the worst possible moment. Your infrastructure must be able to self-heal through expiration.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 75. You migrated to a reactive web flux stack to handle 100K concurrent users, but during a database slowdown, the entire API gateway froze. You find that a developer introduced a blocking I/O call synchronous file read inside the reactive pipeline. How do you unblock the event loops?
Answer: this is an event loop starvation incident. Blocking the Netty threads is fatal to reactive performance. I would resolve it as follows. 1. Diagnosis. Use the Blockhound library in your unit and integration tests. Blockhound will throw an error the moment a blocking call is detected on a non-blocking thread, catching the issue before it hits production. 2. Remediation. Wrap the blocking call in mono. From callable and explicitly move it to the bounded elastic scheduler. This offloads the blocking work to a separate, sized thread pool designed for I/O. 3. Architectural fix. Replace the synchronous file API with an asynchronous alternative like Java NIO or vert.x file system to keep the entire pipeline non-blocking from end to end. Pro tip: Netty event loops are the chosen few. If you have 8 cores, you only have 8 event loop threads. If you block all 8 with a 5-second I/O call, you have effectively taken your entire multi-million-dollar platform offline. Here is Java code demonstrating how to use the bounded elastic scheduler to safely offload blocking I/O calls within a reactive web flux pipeline. Disclaimer: always test code in a non-production environment. This code is the safety valve. It ensures that the blocking file operation is executed on a specialized thread pool that can grow and shrink, preventing the critical Netty event loops from being pinned.
Production Incident 76. A multi-tenant banking app is suffering from request contamination. Customer A occasionally sees customer B's balance. Investigation shows that the user context was stored in a thread local, but because the thread pool was reused, the context from the previous request was still present. How do you sanitize the thread state?
Answer: this is a thread context leak caused by improper pool management. In a pooled environment, threads are immortal. If you do not call .remove on a thread local, the data survives into the next request handled by that thread. I would immediately implement a mandatory cleanup in a servlet filter or an AOP aspect using a finally block to ensure .remove is called on every request completion. For a more modern approach, I would migrate to Java 21 scoped values, which are automatically discarded when the execution scope ends, making this type of session bleed physically impossible. Pro tip: thread local is not a variable, it is a hidden field on the thread object. If you are using thread pools, never use thread local without an ironclad finally remove policy, or you will eventually leak sensitive PII across customer sessions.
Production Incident 77. Your microservices node crashes with java.lang. Out-of-memory error. Unable to create new native thread. The OS reports that the Java process has 20,000 active threads, even though your HTTP pool is capped at 200. How do you find the ghost threads?
Answer: this is a native thread exhaustion incident. The app is likely spawning threads outside of managed pools. I would diagnose and fix it as follows. 1. Diagnosis. Run jstack-lp id pipe grep thread.state pipe wc-l to confirm the count. Then look for thread names like thread 12345. This indicates raw new thread.start calls instead of named pool workers. 2. Root cause analysis. Check third-party libraries SDKs, drivers that might be spawning their own internal heartbeat or clean up threads without a limit. 3. Remediation. Wrap all third-party client initializations in singletons. Many developers mistakenly create a new client for every request, and each client spawns its own internal thread pool, leading to exponential thread growth. 4. OS level fix. Check the ulimit-u max user processes setting. Even if the JVM has RAM, the Linux kernel might be blocking new threads due to security limits. Pro tip: unable to create native thread usually means you have hit a Linux kernel limit or ran out of off-heap memory for thread stacks. Always name your thread pools so you can identify the culprit in a JStack dump instantly.
Production Incident 78. An order completion flow is intermittently hanging for 30 seconds. You find that completable future.get is being called inside a thread that is already part of the common fork join pool. This is causing a circular wait where the pool is waiting for itself to finish. How do you break the deadlock?
Answer: this is a pool-induced deadlock. Blocking on a future.get inside the same pool that is supposed to execute the future's tasks is a classic concurrency anti-pattern. I would immediately refactor the code to use non-blocking callbacks like then compose or then accept, which allow the thread to be released back to the pool while waiting for the result. If a blocking wait is absolutely necessary, I would move that specific task to a dedicated thread pool custom executor service to isolate it from the fork join pool and prevent the circular dependency. Pro tip: never use .get or .join inside a fork join pool or a parallel stream. It is the fastest way to trigger a starvation deadlock that is incredibly hard to debug in production. Here is Java code demonstrating how to replace blocking .get calls with non-blocking composition to prevent fork join pool deadlocks. Disclaimer: always test code in a non-production environment. This code registers a callback. Instead of stopping the thread to wait for the result, the thread is freed to do other work, and the JVM will invoke this logic only when the data is ready.
Production Incident 79. A global configuration singleton is returning null or partial data to some threads during startup, while working fine for others. You discover that the double-checked locking pattern was implemented, but the instance variable was not marked as volatile. Why is this causing object corruption?
Answer: this is a memory visibility failure. Without the volatile keyword, the JVM's instruction reordering can allow a thread to see the instance pointer before the constructor has finished initializing the object's fields. Thread A creates the object and publishes the address, but thread B reads the address and tries to access a field that hasn't been set yet. I would immediately add the volatile modifier to the singleton instance variable to enforce a happens before relationship, ensuring no thread can see a partially constructed object. Pro tip: double-checked locking is a dangerous optimization. In modern Java, the initialization on demand holder idiom is the thread-safe, high-performance gold standard for singletons, as it leverages the JVM's internal class loading guarantees.
Production Incident 80. An audit logging service intermittently hangs and stops writing logs. A thread dump shows that a thread acquired a reentrant lock, but died due to an out-of-memory error before it could release the lock. Now, every other thread is blocked forever. How do you fix the orphan lock?
Answer: this is a lock leak incident. The lock was never released because the code was not exception safe. I would resolve this as follows. 1. Immediate fix. Force a restart of the node to clear the orphan lock state. 2. Code remediation. Enforce the lock finally pattern. Every call to lock must be immediately followed by a try block with the unlock call residing strictly inside the finally block. 3. Tuning. Switch to try lock with timeout time unit. This ensures that even if a lock is leaked, other threads will eventually time out and throw an error rather than hanging indefinitely. 4. Architectural shift. Move toward immutable data and atomic references where possible to eliminate the need for manual locking entirely. Pro tip: synchronized blocks are automatically released when an exception occurs, but reentrant locks are not. If you use reentrant lock, you have assumed manual responsibility for the JVM safety. Never skip the finally unlock block.
Category 4 Conclusion. Mastering concurrency orchestration.
Threading is the transmission of your application. As we have seen in these 20 incidents, concurrency failures from deadlocks and lock convoys to event loop starvation are the silent killers of throughput. In a multi-core world, the goal is not to use more threads, but to use threads more efficiently. Mastery in this category means moving beyond synchronized blocks and learning to design for isolation, backpressure, and non-blocking composition. When your threads flow without friction, your platform achieves true scalability.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 4 to Category 5.
But even if your threads are perfectly orchestrated, they can still crash the system by consuming memory that the garbage collector cannot see. If the heap is the managed garden of the JVM, then native memory is the wilderness outside the fence. When this off-heap space overflows, the JVM does not just slow down, it often disappears entirely without a trace in the standard logs. We now move from the managed heap to the hidden world of native memory and off-heap incidents. Let's explore Category 5.
Category 5. Native memory and off-heap incidents.
Native memory is where high-performance Java meets the operating system. In this category, we move beyond the -XMX limit into the world of direct byte buffers, metaspace, and JNI. We will analyze the ghost leaks that cause Kubernetes to kill your pods even when heap usage is low. We test your ability to use native memory tracking NMT and system-level profilers to find the unreleased buffers and class loader leaks that threaten the very stability of the JVM process.
Category 5. Native and off-heap production incidents 81 to 90.
Here are the 10 scenarios covering the hidden memory leaks and native crashes. Production Incident 81. Direct byte buffer leak exhausting native memory and crashing nodes. Production Incident 82. Netty pooled allocator retaining unreleased buffers in high-load clusters. Production Incident 83. JNI library causing a native segmentation fault in the core banking app. Production Incident 84. JVM crashed with a SIG-SEG during heavy native code execution. Production Incident 85. Metaspace exhaustion after an explosion of dynamic proxy creation. Production Incident 86. Class loader leaks preventing class unloading and saturating RAM. Production Incident 87. Native memory tracking NMT disabled during a critical leak investigation. Production Incident 88. Off-heap cache consuming node RAM unexpectedly beyond capacity. Production Incident 89. Memory mapped files mmap exhausting virtual memory address space. Production Incident 90. Unsafe API misuse causing silent memory corruption and fatal crashes. Total 10 incidents for native memory and off-heap. Let's start with Production Incident 81.
Production Incident 81. Your high-throughput file gateway is being killed by Kubernetes, even though your heap usage is steady at only 4 GB of its 8 GB limit. Analysis of the OS RSS shows the process is consuming 14 GB of RAM. What is your troubleshooting approach?
Answer: this is a direct memory leak incident. The JVM is allocating memory outside the heap that the GC does not proactively manage. I would resolve it as follows. 1. Immediate action. Enable native memory tracking using -XX native memory tracking equals detail and restart the pod to begin capturing the specific off-heap allocation site. 2. Root cause analysis. Use jcmd_pidvm.native_memory summary to see the internal and other categories. If internal is growing, it is likely unreleased byte buffer.allocate direct calls. 3. Code remediation. Ensure all direct byte buffers are being cleaned. Unlike heap objects, they are only reclaimed when the cleaner thread runs. I would explicitly set -XX max direct memory size to a value lower than the container limit to force a Java before Kubernetes kills the pod. 4. Alternative. Replace manual direct buffer management with a pooled approach like Netty's byte buff allocator to ensure buffers are recycled rather than leaked. Pro tip. Kubernetes killer only sees process RSS, but the JVM GC only sees heap. If your direct memory is not capped, your JVM will keep allocating until the OS murders it. Always set -XX max direct memory size to prevent silent infrastructure crashes. Here is JVM configuration, demonstrating how to enable native memory tracking, and cap direct memory to prevent silent container-level kills. Disclaimer: always test code in a non-production environment. This code sets a hard limit on off-heap allocations. By capping this, the JVM will throw a java.lang. out of memory error. Direct buffer memory instead of allowing the OS to kill the process without a stack trace. Here is the code enabling the diagnostic engine. This allows you to use JCMD to see exactly which JVM subsystem code cache, metaspace, or internal is consuming the native memory.
Production Incident 82. A streaming analytics platform is experiencing a gradual RAM creep of 1 GB per day. Thread dumps show no memory leaks in the heap, but the Netty pooled allocator is reporting thousands of active but unreleased chunks. How do you resolve the Netty buffer leak?
Answer: this is a reference counting failure. Netty uses pooled buffers that must be explicitly released via reference count util.release with MSG because the Java GC cannot see their pooled lifecycle. I would immediately implement a leak detection level by setting the system property -do.netty.leakDetection.level equals advanced. This will log a stack trace of the exact line of code where the buffer was allocated but never released. I would then ensure that every handler in the Netty pipeline has a finally block to release the buffer, or uses a simple channel inbound handler which handles the release automatically. Pro tip: Netty performance comes from manual memory management. If you forget to call .release, you are not just leaking memory, you are poisoning the pool, which eventually leads to a fatal allocation failure under high load.
Production Incident 83. A legacy core banking application uses a custom C++ JNI library for high-speed encryption. During a security audit, the JVM suddenly disappeared, leaving a hs_error_pid.log file showing a SIG-SEGV in a native library address. How do you stabilize the native Java bridge?
Answer: this is a native memory corruption incident. A segmentation fault means the C++ code attempted to access memory it didn't own. I would resolve it as follows. 1. Analysis. Open the hs_error_pid.log and identify the problematic frame. If it is inside the custom .so or .dll file, the bug is in the C++ code, not the Java code. 2. Root cause. The Java code likely passed a null or invalid pointer or buffer to the JNI method, or the C++ code had a buffer overflow that corrupted the JVM's internal memory structures. 3. Remediation. Implement strict input validation in the Java layer before calling any JNI method. Use byte buffer is direct to ensure the memory is accessible to the native side. 4. Architectural shift. Move the native logic to a separate sidecar process and communicate via Unix domain sockets or shared memory. This ensures that if the native code crashes, it does not take down the entire JVM. Pro tip: JNI is a death pact. If the native code makes one mistake, the JVM dies instantly. For modern apps, prefer the foreign function and memory API project Panama in Java 22+. It is safer and provides better performance than legacy JNI.
Production Incident 84. Your global search engine crashed with a SIG-SEGV during a peak hour index refresh. The crash log points to a deoptimization event in the JIT compiler. How do you determine if this is a JVM bug or an application failure?
Answer: this is a fatal JVM error incident. Because the crash happened in the JIT compiler C2 and not an application code, it is likely an internal JVM bug or a hardware fault like bad RAM. I would first try to isolate the problematic method by using the -xx compile command =exclude com.myip.search process flag to stop the JIT from compiling that specific method. If the crashes stop, I would report the issue to the open JDK community and plan an immediate upgrade to the latest JDK patch release, which likely contains a fix for this edge case compiler crash. Pro tip: a SIG-SEGV in the JIT compiler is the blue screen of death for Java. Before you rewrite your code, check your JDK version. 99% of these crashes are solved by simply updating to the latest minor patch, for example, from 17.0.2 to 17.0.12.
Production Incident 85. A dynamic routing service crashed with java.lang. Out-of-memory error. Metaspace. Metrics show that metaspace usage grew linearly from 200 megabytes to 2 gigabytes over 4 hours. You find that the app is using a library that generates dynamic proxies for every incoming HTTP request. How do you fix the class bloat?
Answer: this is a metaspace leak caused by infinite class generation. I would resolve the exhaustion as follows. 1. Immediate fix. Set a hard limit using -XX max metaspace size equals 512 megabytes. This prevents the metaspace from consuming the entire node's RAM and forces an that is easier to debug. 2. Root cause. Dynamic proxies like those from Spring or Hibernate create new class objects. If these are not cached and reused, the metaspace which stores class metadata will grow forever. 3. Remediation. Refactor the proxy generation logic to use a cache based on the target class type. This ensures that only one proxy class is generated per service, rather than one per request. 4. Verification. Use JStat-GCP-ID to monitor the MU metaspace utilization. After the fix, the MU should stay flat after the initial startup period. Pro tip: metaspace is for static metadata. If you see it growing continuously, you are generating code at runtime. In a healthy JVM, metaspace usage should plateau within 10 minutes of startup. Here is Java code demonstrating how to use a static cache for dynamic proxies to prevent metaspace exhaustion from redundant class generation. Disclaimer: always test code in a non-production environment. This code implements the canonical cache pattern. By storing the generated proxy instances in a static map, we ensure that the JVM only generates and loads the proxy bytecode once per type.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 86. Your microservices plugin system supports hot reloading of jar files. However, after 10 reloads, the JVM crashes with an You find that old class loaders are never being garbage collected because a static map in the parent class loader is still holding references to objects from the child class loader. How do you break the leak?
Answer: this is a class loader leak, one of the hardest Java bugs to find. When a parent class loader holds a reference to an object from a child, the entire child class loader and all the classes it loaded is pinned in memory. I would immediately implement a shutdown hook in the plugin system to clear all static references, listeners, and thread locals during the unload phase. I would also use Eclipse Mat to find the path to GC root for a leaked class. The leaking reference is usually a static field or a running thread that was not properly terminated. Pro tip: if you build a plugin system, clean shutdown is more important than fast startup. If you do not nullify every reference during an unload, your metaspace and heap will eventually become a graveyard of dead class loaders.
Production Incident 87. During a critical outage investigation of a native memory leak, the SRE team realized that native memory tracking NMT was disabled in the production JVM flags. They tried to enable it via JCMD, but the JVM returned an error, saying it can only be enabled at startup. How do you design for always-on diagnostics?
Answer: this is a diagnostic readiness failure. You cannot diagnose a native leak after it starts without NMT. I would handle this as follows. 1. Policy change. Enforce -XX native memory tracking equals summary as a mandatory flag for all production JVMs. The CPU overhead is less than 1%, but it provides the visibility needed for emergency triage. 2. Automation. Add a step in the CI and CD pipeline that validates the presence of NMT flags in the Kubernetes deployment YAML. 3. Proactive monitoring. Use a sidecar or a cron job to periodically run JCMD PIDVM.native_memory baseline and diff. This allows you to catch native leaks in the staging environment before they ever hit production. 4. Alternative. If NMT is off, use OS-level tools like pmap-x or valgrind on dev to see the memory mappings of the process. Pro tip: NMT is your X-ray for the JVM process. Running production without NMT is like flying a plane without an altimeter. The 1% performance cost is the insurance premium you pay for 100% visibility into native RAM.
Production Incident 88. Your in-memory fraud cache uses an off-heap storage engine to avoid GC pauses. However, the node suddenly crashed without memory, even though the JVM heap and the cache limits were correctly set. You find that the off-heap engine failed to account for memory fragmentation overhead. How do you resize the node?
Answer: when you allocate 10 gigabytes off-heap, the OS might actually use 12 gigabytes due to fragmentation and page alignment. I would immediately increase the Kubernetes memory limit to be 30% higher than the sum of XMX plus max direct memory. I would also switch the native allocator to Gemalloc, which is significantly more efficient at managing fragmentation than the default glibc allocator for high concurrency Java applications. Finally, I would implement a safety margin in the cache configuration, capping it at 70% of the available native space. Pro tip: 10 gigabytes of data does not mean 10 gigabytes of RAM. Always assume a 20 to 30% fragmentation tax when using off-heap storage. If you size your containers too tightly, the OS will kill your process during a peak allocation surge.
Production Incident 89. A log processing JVM is crashing without memory error. Map failed when trying to read thousands of small files. Metrics show the JVM is nowhere near its RAM limit, but the virtual memory address space is exhausted. How do you resolve mmap exhaustion?
Answer: this is a virtual address space or file descriptor incident. I would resolve the exhaustion as follows. 1. Root cause. The application is using mapped byte buffer to read files. Each mapping consumes a virtual memory area VMA. Linux has a default limit vm.max_map_count of 65,530. If you exceed this, mmap calls will fail even if you have free RAM. 2. OS fix. Immediately increase the limit by running sysctl-wvm.max_map_count equals 262144 on the host nodes. 3. Code fix. Refactor the log processor to batch the file processing, or use a standard file channel .read for small files instead of mapping them, which reduces the pressure on the kernel's VMA table. 4. Monitoring. Add a check for /proc/self/maps to see how many memory segments the JVM is currently holding. Pro tip: map failed is the most confusing error. It almost always means you hit a kernel limit on the number of memory mappings, not that you ran out of physical RAM. Check your vm.max_map_count first.
Production Incident 90. An ultra-low latency library uses the internal sun.misc.unsafe API to perform manual memory management. During a high-load event, the JVM crashed with a sig-seg. You find that the code was performing use after free, attempting to write to a native address that had already been deallocated. How do you secure unsafe code?
Answer: this is a manual memory management failure. The unsafe API provides no guardrails. A single wrong address will cause a fatal crash or, Worse, silent data corruption. I would immediately initiate a migration to the foreign function and memory API project Panama available in Java 21+. Panama provides arena and segment abstractions that are scope safe. The JVM will throw a predictable Java exception if you try to access deallocated memory, rather than crashing the entire process. In the short term, I would implement strict lifecycle ownership in the unsafe-based code, ensuring that only one thread is responsible for the allocation and deallocation of a specific memory block. Pro tip: sun.misc.unsafe is deprecated for a reason. In modern days, using it is an architectural liability. Project Panama gives you the same C-level speed, but with Java-level safety and error reporting.
Category 5 Conclusion: Managing the Invisible Foundations.
Native memory is the final frontier of JVM stability. As we've seen in these 10 incidents, the garbage collector is powerless against leaks in direct byte buffers, Netty pools, and metaspace. Mastery here means acknowledging that the JVM is a guest on an operating system. By using native memory tracking and modern APIs like Panama, you ensure that your application does not just survive within its heap, but thrives within the strict resource boundaries of your enterprise infrastructure.
The universal interview tip: whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip: get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 5 to Category 6.
But even a memory-stable JVM is useless if it takes 15 minutes to start or crashes during the first wave of traffic. If native memory is the foundations, then startup and JIT compilation are the ignition and acceleration. In a world of serverless and auto-scaling Kubernetes clusters, your time to ready is a business-critical metric. We now move from the memory structures to the high-stakes world of JVM startup, deployment, and JIT compiler incidents. Let's explore Category 6.
Category 6. JVM Startup, Deployment, and JIT Incidents.
JVM startup and JIT just-in-time compilation represent the bridge between cold bytecode and hot native performance. In this category, we dive into the war stories of 14-minute Spring Boot startups, circular dependency deadlocks, and the latency spikes caused by JIT de-optimization storms. We test your ability to use app CDS and tiered compilation to ensure your services are ready to handle production traffic the moment they pass their health check.
Category 6. Startup and JIT Production Incidents 91 to 100.
Here are the 10 scenarios covering deployment disasters and compilation bottlenecks. Production Incident 91. Spring Boot startup time increased to 14 minutes in a cloud environment. Production Incident 92. Circular bean dependencies causing a silent startup deadlock. Production Incident 93. JIT compiler performance regression after a major JDK upgrade. Production Incident 94. Excessive class path scanning slowing down service initialization. Production Incident 95. Dynamic bean creation exhausting metaspace during deployment. Production Incident 96. Class verification delays increasing deployment times on large jars. Production Incident 97. Third-party bytecode agents breaking the JVM startup sequence. Production Incident 98. Tiered compilation behaving inconsistently after a platform migration. Production Incident 99. Warm-up latency causing 503 errors during Kubernetes auto-scaling. Production Incident 100. CDS archive incompatibility causing JVM startup failures in production. Total 10 incidents for startup and JIT. Let's start with Production Incident 91.
Production Incident 91. Following a massive migration to a micro-monolith architecture, your Spring Boot startup time increased from 45 seconds to 14 minutes. This has paralyzed the CI and CD pipeline and made emergency patching impossible. How do you reduce the startup friction?
Answer: this is a startup complexity failure. The JVM is spending too much time on JIT compilation and metadata processing before the app is ready. I would optimize this as follows. 1. Diagnosis. Use the -XX plus print compilation and -XX plus unlock diagnostic VM options -XX plus print inlining flags to see if the JIT is struggling with a massive volume of code during startup. 2. Immediate fix. Disable C2 compilation for the startup phase by using -XX tiered stop at level equals 1. This keeps the JVM in a quick compilation mode, sacrificing peak performance for a 5 times faster startup time. 3. Architectural remediation. Enable app CDS application class data sharing. This allows the JVM to map preprocessed class metadata into memory from a shared archive, eliminating the need to parse and verify thousands of jars on every start. 4. Spring optimization. Implement @Spring Boot application with proxy bean methods equals false and use context indexing to replace expensive runtime class path scanning with a pre-computed index created at build time. Pro tip: 14-minute startups are usually caused by the JIT trying to optimize code that only runs once. Use app CDS for production and tiered stop at level equals 1 for development to reclaim your agility. Here is JVM configuration demonstrating how to generate and use an app CDS archive to dramatically accelerate Java application startup times. Disclaimer: always test code in a non-production environment. This code, followed by the dump flag, tracks every class loaded during a sample run. This training run tells the JVM exactly which metadata needs to be cached for future speed. Here is the code where the archive is utilized. By mapping the JSA file directly into memory, the JVM bypasses the expensive disk I/O and verification steps for thousands of classes, often cutting startup time in half.
Production Incident 92. Your risk management service is hanging during deployment. The logs stop at refreshing application context, and the CPU is at 0%. A thread dump shows that the main thread and a background worker thread are blocked while attempting to initialize 2 different beans that have a circular dependency. How do you resolve a startup deadlock?
Answer: this is a lazy initialization deadlock. When Spring attempts to resolve circular dependencies using multiple threads common in asynchronous bean initialization, it can enter a state where thread A is waiting for bean B's lock, while thread B is waiting for bean A's lock. I would first disable asynchronous initialization for the affected beans to force a deterministic, single-threaded startup. I would then refactor the architecture to replace field injection with constructor injection, which allows the compiler to detect circularities at build time rather than allowing them to become runtime deadlocks in production. Pro tip: circular dependencies are an architectural smell. If you must have them, use the @lazy annotation carefully, but never combine lazy circular beans with parallel context refreshing, or you are guaranteed to have non-deterministic startup hangs.
Production Incident 93. After upgrading from JDK 11 to JDK 21, your price calculation engine is 20% slower. Profiling shows that the JIT compiler C2 is failing to inline a critical method that was previously inlined. How do you troubleshoot and fix a JIT regression?
Answer: This is a heuristic change incident. JIT compilers have inlining thresholds that change between versions. I would immediately run the app with -XX plus print inlining to find the inlining failed message for the calculation method. Usually, the method is now considered too big for the new version's default limit. I would either refactor the method to be smaller below 35 nodes to satisfy the monomorphic inlining rule, or increase the -XX max freak inline size flag to force the compiler to accept the larger method. Restoring that single inlining decision will typically recover the 20% performance loss. Pro tip: JIT inlining is the single most important optimization in Java. If a method is not inlined, it cannot be escaped, analyzed, or vectorized. Use JITwatch to visualize your compilation logs and ensure your hot paths are always inlined.
Production Incident 94. A core banking app is spending 3 minutes in classpath scanning before the first log line appears. You discover that the application has 1,200 jar dependencies, and Spring is scanning every single one of them for @component annotations. How do you optimize the scan?
Answer: this is an ingestion phase bottleneck. I would move the scanning from runtime to compile time. 1. Immediate fix. Explicitly define the base packages and @component scan with base packages equals to stop Spring from scanning the root directory and third-party libraries. 2. Remediation. Use the Spring context indexer dependency. This generates a meta inf/spring.components file during the build, which Spring uses to instantly find beans without scanning any jars at runtime. 3. Refinement. Transition to functional bean definitions if using Spring 5+, which bypasses the annotation processor entirely and is the fastest way to wire a Java application. 4. Verification. Monitor the startup time metric in your CI and CD pipeline to ensure the classpath scanning overhead remains under 5 seconds. Pro tip: classpath scanning is an big O of N operation. As your dependency list grows, your startup time will grow linearly. Use a static index to make your startup time big O of 1 relative to the number of jars.
Production Incident 95. Your dynamic pricing engine allows users to upload Groovy scripts as custom rules. During a heavy deployment, the JVM crashed with Metaspace It appears that every script execution is creating a new dynamic bean and class loader that are never cleaned up. How do you secure the metaspace?
Answer: this is a metadata leak caused by script bloat. Every time Groovy or a similar dynamic language evaluates a script, it generates a new Java class. If these scripts are not cached, they fill the metaspace until the JVM crashes. I would immediately implement a script cache using a unique hash of the script content as the key, ensuring each script is compiled into a class exactly once. I would also set a strict -XX max metaspace size to ensure that a leak in the script engine does not bring down the entire node RAM, and I would configure a script reaper that clears the cache for rarely used rules to allow class loaders to be garbage collected. Pro tip: never use eval.me or new Groovy class loader.parse class in a high-frequency loop. Always use a cached script engine, and verify that your metaspace usage remains flat even after 10,000 script executions.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, You can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 96. A legacy gateway with a 400 megabytes monolithic jar is taking 5 minutes to start. JFR logs show that class verification is responsible for 60% of the delay. The security team insists on verification, but the business needs faster restarts. How do you balance speed and security?
Answer: this is a bytecode validation bottleneck. Verification ensures that bytecode does not violate JVM safety rules, but it is slow for large apps. I would optimize it by 1. Standard fix. Use app CDS as seen in Incident 91. Once a class is verified and stored in the CDS archive, the JVM skips verification on subsequent restarts because the archive is already trusted. 2. Temporary fix. If in a trusted internal cloud environment, use -xverify:null to skip verification entirely. Note: this is deprecated and highly risky if you load third-party plugins. 3. Architectural fix. Modularize the monolithic jar. Smaller jars allow the JVM to verify classes in parallel more efficiently and reduce the hotspot of metadata processing during the initial boot sequence. 4. Verification. Check the -verbose: class output to see if there is an unusual amount of loading and verifying for classes that are never actually used. Pro tip: class verification is a compute tax. The best way to avoid it is to use CDS class data sharing. It gives you the security of full verification during the dump phase and the speed of zero verification during the production phase.
Production Incident 97. After adding a new security scanning agent Java agent to your production cluster, 20% of your pods failed to start. The logs show a no class def found error for core Spring classes. How do you troubleshoot an agent-induced startup failure?
Answer: this is a class loader hierarchy conflict. Java agents run in the system class loader and use bytecode instrumentation to rewrite classes as they load. If an agent tries to reference an application class before the application class loader is ready, it triggers a crash. I would immediately remove the agent to restore service. For a permanent fix, I would use the -xlog: class plus load equals info flag to find the order of operations during boot. I would then refactor the agent to use lazy instrumentation or shading to ensure the agent's dependencies do not collide with the application's dependencies. Pro tip: Java agents are God objects in the JVM. They can see and change everything. When an agent breaks your startup, it is usually because it tried to load a class too early. Always place your agents behind an enable or disable flag in your deployment YAML.
Production Incident 98. A payment service is experiencing bimodal performance. After a restart, the first 5 minutes of requests take 500 milliseconds, then suddenly they drop to 10 milliseconds. You discover that tiered compilation is staying in level 3 profiled C1 too long before moving to level 4 C2. How do you accelerate the warm-up?
Answer: this is a JIT leveling issue. The JVM is taking too long to decide that the code is hot. I would accelerate the transition via 1. Tuning. Decrease the -XX compile threshold and -XX tier 3 invocation threshold. This forces the JIT to promote code to see level 4 much earlier in the application's life. 2. Warm-up script. Implement a synthetic traffic phase in your Kubernetes startup probe. Send 1,000 dummy requests to the most critical endpoints before marking the pod as ready. 3. Hardware alignment. Check if the node has enough CPU cores. JIT compilation happens in background threads. If the node is CPU starved during startup, the JIT threads will be deprioritized, extending the cold period indefinitely. 4. Verification. Use jstat-compiler to monitor the number of compiled methods. If the count stops growing, the warm-up is complete. Pro tip: tiered compilation is standard, but the defaults are optimized for long-running servers. For fast-scaling microservices, You should lower your compilation thresholds to reach peak performance 3 times faster.
Production Incident 99. Your auto-scaling group added 10 new nodes to handle a traffic spike, but all 10 nodes immediately hit 100% CPU and began failing 50% of requests. This is warm-up latency destroying your scaling strategy. How do you make your auto-scaling safe?
Answer: this is a cold start saturation. A newly started JVM is interpreting bytecode, which is 10 times to 50 times slower than compiled native code. When the load balancer hits a cold node with 100% traffic, the CPU saturates before the JIT can finish its work. I would immediately implement linear warm-up at the load balancer level like AWS ALB slow start or engine X-wait. This sends only 10% of traffic to a new node, gradually increasing to 100% over 2 minutes, giving the JIT compiler enough CPU headroom to compile the hot paths without crashing the node. Pro tip: auto-scaling without a warm-up period is a recipe for disaster. Your peak performance is irrelevant if your startup performance cannot survive the first 60 seconds of production load. Here is JVM configuration, demonstrating how to use JFR Java Flight Recorder to identify and visualize JIT compilation bottlenecks during the application warm-up phase. Disclaimer: always test code in a non-production environment. This code followed by the JFR recording capture. By recording the first 5 minutes, we can see exactly which methods are being compiled, and if the JIT threads are competing with business threads for CPU. This code, followed by the compilation log flag, provides a detailed XML file of every JIT decision. This is the source of truth for identifying why specific methods are failing to inline or are being repeatedly de-optimized.
Production Incident 100. You successfully implemented app CDS class data sharing in staging, but in production, the JVM fails to start with the error the shared archive file has a different version than the current JVM. How do you manage CDS in a CI and CD environment?
Answer: this is a metadata mismatch failure. CDS archives are extremely sensitive to the exact JVM version and the class path order. If your production Docker image uses a slightly different patch version of OpenJDK, for example, .0.1 versus .0.2, or the jar files are in a different order, the archive is invalidated. I would immediately update the CI and CD pipeline to generate the CDS archive inside the final production container as part of the build process. This ensures that the JVM and the archive are perfectly matched, guaranteeing 100% startup reliability across every regional cluster. Pro tip: never ship a CDS archive as a separate artifact. It must be bailed into the Docker image alongside the specific JVM that will run it. This eliminates the version drift that causes mysterious startup failures in production.
Category 6 Conclusion. Mastering the ignition of the JVM.
Startup and JIT compilation are where the cold application meets the hot reality of production traffic. As we've seen in these 10 incidents, a failure at this stage, from 14-minute Spring Boot boots to JIT regressions, can paralyze your ability to scale and recover from outages. Mastery here means moving beyond the defaults to use modern tools like app CDS and tiered compilation tuning. By ensuring your time to ready is as fast as your peak throughput, you build a truly resilient, cloud-native Java architecture.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 6 to Category 7.
But sometimes, a service does not just slow down, it vanishes. While a memory leak or a slow thread pool gives you time to react, a JVM crash is instant and absolute. When you see a SIG-SEV or an HS_error_PID log, you are no longer dealing with Java code. You are dealing with a failure of the machine itself. We now move from the execution lifecycle to the most high-stakes domain of all, JVM crash and fatal error incidents. Let's explore Category 7.
Category 7. JVM crash and fatal error incidents.
A JVM crash is the blue screen of death for Java engineers. In this category, we dive into the catastrophic failures that leave no stacked trace in your standard logs, only a cryptic fatal error file. We will analyze native memory corruption, hardware faults like bad RAM, and the internal JVM guarantee failures that occur when the runtime's own assumptions are violated. We test your ability to read the HS_error logs to determine if the crash was caused by your code, a third-party library, or a failure of the underlying infrastructure.
Category 7. JVM crash production incidents 101 to 108.
Here are the 8 fatal error scenarios covering native crashes and hardware failures. Production Incident 101. SIG-SEV in native or JNI code generating an HS_error_PID.log file. Production Incident 102. JVM internal error guarantee failure during a critical GC cycle. Production Incident 103. Fatal crash due to undetected bad RAM or hardware bit rot. Production Incident 104. JVM crashes occurring during class unloading or metaspace cleanup. Production Incident 105. Out-of-memory error in native thread stack allocation crashing the OS process. Production Incident 106. Core dump generation failure due to strict container size limits. Production Incident 107. JVM aborted instantly due to the -XX+ exit on out-of-memory error trigger. Production Incident 108. Segmentation fault in GC worker threads after large-scale heap tuning. Total 8 incidents for JVM crashes. Let's dive into the forensics of Production Incident 101.
Production Incident 101. Within 5 minutes of a traffic surge, your identity verification service crashed without a single Java exception. The only artifact left was a 200 kilobytes HS_error_PID.log file showing a SIG-SEV signal 11 in a native library called libcrypto.so. How do you perform the forensics to resolve this crash?
Answer: this is a native memory access violation. I would immediately open the HS_error file and look for the problematic frame. If the crash happened in a native library like OpenSSL or a custom JNI bridge, it indicates that the Java code passed an invalid memory address or a null pointer to a native function. I would analyze the register values in the log to see if a 0x00000000 address was accessed. To resolve this, I would add strict null checks and boundary validation on the Java side before the JNI call, ensuring the native layer is never invoked with invalid data that could crash the entire process. Pro tip: the HS_error_PID.log is your only source of truth during a crash. Always look at the virtual machine version and the native frames first. If the crash is in a .so or .dll, the bug is likely in how your Java code interacts with that library, not in the JVM itself.
Production Incident 102. During a high-load batch run, your JVM aborted with an internal error stating guarantee with false failed. This is a fatal assertion inside the JVM code itself. How do you handle an incident where the runtime breaks its own rules?
Answer: this is a JVM intrinsic failure. The JVM detected an internal inconsistency it could not recover from. I would handle this via 1. Forensics. Extract the internal error message from the fatal error log. A guarantee failure means a developer at Oracle or OpenJDK added a safety check that was violated. 2. Immediate action. Check for bit flip patterns in the log. If the error is non-reproducible and occurs on different methods, it is likely a hardware or OS memory issue. 3. Workaround. Try disabling specific JIT optimizations, for example, -xx compile command equals exclude com/app/my method if the log points to a specific method during compilation. 4. Escalation. Package the HS_error log, the core dump, and the JVM version details into a bug report for the OpenJDK community, as this is likely a bug in the runtime engine. Pro tip: internal errors are rare but terrifying. If you see guarantee or assert failures, you have found a corner case the JVM developers didn't expect. Always check if a newer patch version of the JDK, for example, 17.0.8 to 17.0.9, already contains a fix for that specific internal crash.
Production Incident 103. A stock trading JVM is crashing once a week with a SIGBUS or SIG-sev error, but the crash address is different every single time. It seems to happen randomly across different worker nodes. What is your troubleshooting approach for stochastic crashes?
Answer: this is a hardware-level corruption incident. When crashes are random and have no consistent problematic frame, it is a primary indicator of bad RAM bit rot. I would immediately look for machine check exceptions MCE in the Linux kernel logs using DMESG or journal CTL. If the kernel reports hardware error or ECC memory corrected, I would replace the physical DIMM or move the workload to a different cloud instance. These crashes occur because a single bit in RAM was flipped, turning a valid memory pointer into trash that the JVM cannot follow. Pro tip: if your JVM crashes randomly in different libraries and methods, stop debugging your Java code. Run memtest86 or check your cloud provider's health dashboard. 90% of non-reproducible SIG-sevs are caused by failing hardware, not software bugs.
Production Incident 104. Your plugin engine is crashing during periods of low traffic when the JVM attempts to perform class unloading. The crash occurs in the metaspace management code. How do you resolve a crash that happens while the JVM is trying to clean up metadata?
Answer: this is a metadata corruption failure. The JVM is crashing while trying to free memory used by old class loaders. I would fix it as follows. 1. Root cause analysis. Usually this is caused by a native agent like an APM tool that holds a dangling pointer to a class that has been unloaded, causing the JVM to crash when it tries to access the metadata. 2. Immediate fix. Temporarily disable class unloading using -xx- class unloading to stop the crashes, though this will eventually lead to a metaspace 3. Investigation. Use the HS_error log to see if a Java agent was active during the crash. If libupum_agent.so is in the stack, the agent is likely incompatible with the current JDK's metaspace structure. 4. Remediation. Upgrade the monitoring agent to a version that supports safe class unloading or refactor the application to use a more stable class loader lifecycle. Pro tip: class unloading is a dark corner of JVM performance. If you have a high churn of classes, for example, dynamic groovy scripts, you are 10 times more likely to hit these crashes. Keep your class count stable to keep your JVM safe.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 105. An asynchronous search service crashes with an error, but the logs say unable to create new native thread. You have 16 gigabytes of free heap, but the JVM cannot allocate memory for the thread stack. How do you resolve this native memory exhaustion?
Answer: this is a stack memory incident. Every Java thread requires its own native memory stack, usually 1 megabytes per thread. If you have 2,000 threads, you are using 2 gigabytes of native RAM just for stacks, which sits outside the heap. I would immediately check if the application is leaking threads incident 77, or if the -XSS thread stack size is set too high. I would reduce the -XSS to 512K or 256K to double the number of threads that can fit in the available native memory, and I would move toward virtual threads to eliminate the 1 thread per stack requirement entirely. Pro tip: the JVM heap is only half the story. If your -XMX is too large, it might not leave enough room in the OS for the native thread stacks. Always calculate your total process RAM as heap plus thread count times stack size plus meta space plus direct buffers.
Production Incident 106. Following a fatal crash, your SRE team finds that the core dump file, which is needed for deep debugging, is only 0 bytes. This has made it impossible to see the state of the world during the crash. How do you fix your crash dump architecture?
Answer: this is a diagnostic persistence failure. The OS blocked the generation of the dump file. I would resolve this by 1. OS fix. Check the ulimit-c setting on the host and inside the Docker container. If it is set to 0, no core dump will ever be generated. 2. Container fix. Ensure the Kubernetes resource limits account for the core dump. If the JVM has 8 gigabytes of RAM, the core dump will be 8 gigabytes. If the disk or memory limit is smaller, the OS will kill the dump process. 3. Storage fix. Use the -xx error file equals /var/logs/hs_error_pid%p.log flag to ensure the log is written to a persistent volume rather than the container's ephemeral layer. 4. Verification. Run a test crash in a staging environment using kill-6pid to verify that a full, readable core dump is actually created. Pro tip: a 0-byte core dump is a missed opportunity for a permanent fix. In Kubernetes, always set your ulimit-c unlimited in the security context of your pod spec to ensure you have the forensics you need after a crash.
Production Incident 107. A critical payment node was found in a zombie state. It was not processing requests, but the process was still running and passing Kubernetes TCP health checks. You find that the JVM had hit an and the SRE team wants an immediate kill on How do you implement a self-healing crash?
Answer: this is a zombie process failure where a damaged JVM stays alive. I would implement an aggressive exit strategy. 1. JVM flag. Add -xx plus exit on out-of-memory error to the startup script. This tells the JVM to abort immediately the moment the heap is exhausted, rather than trying to survive in a corrupted state. 2. Infrastructure loop. By killing the process, Kubernetes detects the pod failure and automatically restarts a fresh, healthy node, restoring the system's capacity in seconds. 3. Alternative. Use -XX plus crash on out-of-memory error if you want a core dump to be generated times before times the process exits for later debugging. 4. Verification. Ensure that your readiness probes check the actual application health, not just the port status, to detect these zombie states before they impact customers. Pro tip: a dead JVM is better than a zombie JVM. A zombie process continues to hold database locks and consume resources while doing zero work. Always fail fast on so your orchestrator can restart the service. Here is JVM configuration, demonstrating how to enable automatic process exit on out-of-memory error to prevent zombie processes in containerized environments. Disclaimer: always test code in a non-production environment. This code, followed by the exit flag, ensures the JVM process terminates immediately upon an This allows the container orchestrator to notice the failure and restart the pod, preventing a zombie state. Here is the code followed by the dump flag. While the process is exiting, the JVM captures the state of the heap to disk, providing the forensic evidence needed to find the root cause of the memory exhaustion.
Production Incident 108. After tuning your big data JVM for high-throughput G1 GC, you start seeing segmentation fault signal 11 in the GC worker threads. It only happens when you set -XX parallel GC threads to 64. How do you diagnose a GC worker crash?
Answer: this is a threading resource or stack overflow incident in the GC itself. When you have a massive number of GC worker threads, the stack and metadata synchronization becomes highly complex. I would first reduce the number of GC threads to core count times 5 or 8 to see if the crash stops. If it does, it indicates a race condition or stack depth issue in the GC engine. I would then check if transparent huge pages incident 36 is causing memory misalignment that the GC threads cannot handle. And finally, I would update the JDK to the latest security patch to ensure I'm not hitting a known G1 GC bug related to high thread count environments. Pro tip: more GC threads are not always better. Too many threads cause SafePoint jitter and increase the likelihood of hitting rare native synchronization bugs. Stick to the JVM's ergonomic defaults unless your pause times are clearly thread limited.
Category 7 Conclusion. Navigating the fatal horizon.
A JVM crash is the ultimate test of an engineer's forensic ability. As we've seen in these incidents, when the safety of the Java runtime is breached, whether through native memory corruption, hardware bit rot, or internal JVM guarantee failures, there is no stack trace to guide you. Mastery here means being able to reconstruct the crime scene using HS_error logs and core dumps. By stabilizing the native foundations and ensuring your infrastructure is crash-aware, you turn a catastrophic blackout into a manageable diagnostic event.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 7 to Category 8.
But modern Java engineering is not just about preventing crashes. It is about achieving unprecedented scale. If native memory is the foundation, then virtual threads are the skyscrapers of the new Java era. Project Loom has redefined how we think about concurrency, allowing us to manage millions of threads without the OS-level overhead. However, this power comes with its own set of high-altitude risks, like carrier thread pinning and stack chunk bloat. We now move from fatal errors to the cutting-edge world of virtual threads Project Loom incidents. Let's explore Category 8.
Category 8. Virtual Threads Project Loom Incidents.
Virtual Threads Project Loom promised to make high concurrency Java easy, but easy does not mean free of performance risks. In this category, we explore the reality of production Java 21 deployments, where legacy synchronized blocks pin threads and thread local abuse causes silent memory explosions. We test your ability to diagnose carrier thread starvation and your skills in migrating from platform-based threading to a million-thread-ready architecture.
Category 8. Virtual Thread Production Incidents 109 to 116.
Here are the 8 production incidents covering Project Loom failures and Loom-based performance collapses. Production Incident 109. Carrier thread pinning via synchronized blocks nullifying virtual thread benefits. Production Incident 110. Millions of virtual threads causing excessive heap usage through stack chunk accumulation. Production Incident 111. Thread local abuse within virtual threads leading to unexpected memory leaks. Production Incident 112. Legacy libraries with hidden blocking calls starving the underlying carrier threads. Production Incident 113. Standard debugging and profiling tools becoming overwhelmed by millions of virtual threads. Production Incident 114. A virtual thread explosion during a downstream failure event crashing the JVM. Production Incident 115. Subtle deadlocks introduced during the transition from platform threads to virtual threads. Production Incident 116. Scoped values misuse causing unexpected context retention and data leakage. Total 8 incidents for virtual threads. Let's start with the pinning disaster in Production Incident 109.
Production Incident 109. Within 2 hours of migrating your high-throughput banking API to Java 21 virtual threads, you notice that throughput has dropped by 40% and CPU utilization is erratic. Profiling reveals that several carrier threads are pinned because of the use of synchronized blocks around long-running HTTP calls. How do you resolve this pinning bottleneck?
Answer: this is a carrier thread pinning incident. When a virtual thread enters a synchronized block and performs I/O, it pins its underlying carrier thread, preventing the JVM from using that core for other tasks. I would resolve this as follows. 1. Diagnosis. Run the JVM with -djdk.trace pinned threads equals full. This will log a stack trace every time a thread is pinned, identifying the exact synchronized block that is causing the blockage. 2. Immediate fix. Replace the synchronized blocks with reentrant lock. Unlike synchronized, reentrant lock allows the JVM to unmount the virtual thread even while the lock is held, freeing the carrier thread for other work. 3. Code audit. Search the codebase and all third-party dependencies for synchronized I/O. If a legacy library is pinning threads, you must wrap those calls in a separate dedicated platform thread pool to protect your virtual thread ecosystem. 4. Verification. Ensure that carrier thread utilization remains steady and that the trace pin threads log is clean after the migration to reentrant lock. Pro tip: synchronized is the enemy of Loom. In Java 21, synchronized blocks do not support yielding on I/O. If you want to use virtual threads, your first task is to refactor your locks to reentrant lock to keep your carrier threads liquid. Here is Java code demonstrating the transition from synchronized blocks to reentrant lock to prevent carrier thread pinning in virtual thread environments. Disclaimer: always test code in a non-production environment. This code initializes a modern lock. Unlike the intrinsic synchronized lock, the reentrant lock implementation is Loom aware, ensuring that if the thread blocks on I/O, The underlying OS thread is not held hostage. Here is the code where the I/O occurs. Because we are using reentrant lock, the JVM can successfully unmount the virtual thread and reuse the carrier thread for thousands of other active tasks while the I/O is pending.
Production Incident 110. After scaling your chat service to handle 1 million concurrent users using virtual threads, the JVM crashed with an out-of-memory error. Java heap space. Heap dumps reveal that 90% of the heap is consumed by stack chunks. Why did million thread scalability result in a memory collapse?
Answer: this is a stack chunk accumulation failure. While virtual threads are light, they are not weightless. Their stacks are stored as objects on the Java heap. If your chat threads have deep call stacks, for example, heavy framework nesting, each thread can consume several kilobytes. Multiplied by 1 million, this can easily exceed a 16 gigabytes heap. I would immediately implement a thread cap or use a semaphore to limit the total number of times active times virtual threads to a level the heap can support. For a long-term fix, I would refactor the message processing logic to be shallow, reducing the recursion and stack depth to minimize the size of the stack chunk objects stored in memory. Pro tip: virtual threads are unlimited, but your heap is not. If your business logic has deep call stacks, 1 million threads will kill your JVM faster than platform threads. Always monitor the java.lang.continuation objects in your heap dump to see your real stack overhead.
Production Incident 111. A multi-tenant SaaS application migrated to virtual threads, but within 24 hours, the memory usage tripled. You find that the application uses thread local to store large user permissions objects. Why is thread local dangerous in a virtual thread world?
Answer: this is a metadata scale failure. In a platform thread model, you have a few hundred threads, so a few hundred thread local objects are manageable. In a virtual thread model, you have 100,000 threads, which means you now have 100,000 user permissions objects in memory. I would immediately migrate the application to scoped values introduced in Java 21. Scoped values are immutable, can be shared across child threads efficiently, and are designed to automatically disappear when the task ends, reducing the memory footprint of context data by over 95% compared to millions of legacy thread local instances. Pro tip: thread local is a relic of the platform thread era. In the age of Project Loom, thread locals are memory leaks waiting to happen. Use scoped values for request context. It is safer, faster, and Loom optimized.
Production Incident 112. Your enterprise search service is using virtual threads, but you find that the carrier thread pool fork join pool is completely starved. A third-party security jar is making native JNI calls that block the OS thread without notifying the JVM. How do you resolve invisible blocking?
Answer: this is a native I/O starvation incident. The JVM cannot yield a thread that is blocked inside a native call. I would resolve this as follows. 1. Root cause analysis. JNI calls and some file I/O operations on older Linux kernels do not support the Loom yield mechanism, meaning they behave like platform threads and park the entire carrier thread. 2. Immediate fix. Increase the carrier thread pool size using -djdk.virtualthreadscheduler.parallelism. This provides more spare OS threads to handle the native blocking. 3. Remediation. Wrap the native library calls in a standard executors.new fixed thread pool platform threads. This ensures that the native blocking is isolated and does not steal resources from the main virtual thread scheduler. 4. Governance. Audit all JNI-based dependencies. If they do not have a non-blocking or Loom-compatible version, they must be treated as dangerous resources and restricted to a legacy thread pool. Pro tip: not all blocking is Loom blocking. Native calls, /dev/random access, and some file I/O are hard blocks that the JVM cannot optimize. Always isolate these hard blocks on platform threads to keep your virtual thread engine running.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 113. During a live troubleshooting session, your diagnostic dashboard and JVM crashed while trying to display a thread dump. You have 800,000 virtual threads running. How do you perform scale-aware debugging in Java 21?
Answer: this is an observability saturation failure. Standard tools and thread dumps are designed for hundreds of threads, not millions. Trying to generate a text-based thread dump for 800,000 threads will overwhelm the JVM's memory and the tool's parser. I would immediately switch to using the new thread dump format JSON via jcmd PID thread.dump underscore to underscore file dash format equals JSON. This is significantly more efficient. For real-time monitoring, I would use JDK Flight Recorder JFR to sample thread activity rather than trying to list every individual thread, allowing me to see the state of the system without crashing my diagnostic tools. Pro tip: stop using JStack for virtual threads. It is a legacy tool. Use JCMD with the JSON format or JFR. In the Loom era, you debug thread summaries and aggregates, not individual thread IDs.
Production Incident 114. A retry storm on a downstream payment gateway caused your virtual thread count to explode from 1,000 to 2 million in 30 seconds. This thread explosion triggered a massive GC event that crashed the cluster. How do you implement virtual thread backpressure?
Answer: this is an unbounded concurrency failure. Because virtual threads are cheap, developers often forget to limit them. I would fix this as follows. 1. Immediate action. Implement a semaphore with a fixed number of permits, for example, 10,000. Every virtual thread must acquire a permit before starting its work. 2. Architecture fix. Move away from thread per request for high-risk retries. Use a rate limiter like Resilience 4J to cap the number of outbound calls regardless of how many virtual threads are waiting in the heap. 3. Tuning. Set a max limit on the underlying submission queue to ensure that if the system is overwhelmed, new requests are rejected at the edge rather than creating more thread chunk objects in the heap. 4. Verification. Perform a load test to ensure that during a downstream outage, the thread count stays at a safe ceiling, for example, 50K rather than growing to millions. Pro tip: virtual threads are lightweight, but they are not invisible. 2 million cheap threads are still a massive burden on the garbage collector. Always use a semaphore to keep your concurrency within business boundaries. Here is Java code demonstrating how to use a semaphore to enforce backpressure and prevent virtual thread explosion during downstream outages. Disclaimer: always test code in a non-production environment. This code establishes the concurrency ceiling. By using a semaphore instead of an unbounded thread pool, we ensure that the total number of active virtual threads remains within the heap's safe operating capacity. Here is the code followed by the acquisition check. This provides immediate fast-fail logic. If the system is saturated, it rejects the request instantly rather than creating another virtual thread that would only add to the memory pressure.
Production Incident 115. While migrating a lock-heavy legacy app to virtual threads, you encounter a subtle deadlock that never occurred with platform threads. You find that two threads are now deadlocking because the carrier thread scheduler is reordering tasks in a way the OS scheduler didn't. How do you resolve Loom-specific deadlocks?
Answer: this is a scheduler interaction deadlock. Virtual threads are scheduled by a fork join pool, which uses work stealing and is fundamentally different from the OS time slicing scheduler. I would first identify the lock cycle using a thread dump. To resolve it, I would refactor the code to eliminate nested locks and move toward concurrent data structures. Crucially, I would ensure that any thread performing long-running computation CPU-heavy uses thread.yield periodically to ensure the Loom scheduler can preempt it and allow other threads to progress, breaking the deadlock caused by cooperative multitasking starvation. Pro tip: virtual threads use cooperative scheduling, not preemptive scheduling. If one thread runs a 10-second math loop without I/O, it can hijack a carrier thread and prevent other threads from releasing their locks. Always add thread.yield to your CPU-heavy loops.
Production Incident 116. Your identity service migrated to scoped values for security context, but you find that some child threads are still seeing admin permissions after the parent request has finished. Why is scoped value context being retained, and how do you secure it?
Answer: this is a scope leak failure. Scoped values are designed to be bound to a specific runnable or callable. If you manually pass a scoped value to an async executor that lives outside the scope, or if you misuse the structured task scope, you can experience context bleed. I would immediately refactor the code to use structured concurrency structured task scope. This ensures that the scoped value context is inherited only by child threads that are strictly managed within the parent scope and are guaranteed to be terminated before the parent scope exits, ensuring 100% security isolation. Pro tip: scoped values and structured concurrency go hand in hand. Never use scoped values with legacy executor services or fire and forget async tasks. You will lose the scope and end up with unpredictable context retention. Here is Java code demonstrating the use of scoped values with structured concurrency to ensure safe context inheritance in virtual thread pipelines. Disclaimer: always test code in a non-production environment. This code, followed by the scope initialization, ensures structured concurrency. It creates a hard boundary where all child threads forks must complete before the code proceeds, preventing the context from leaking beyond the request lifecycle. Here is the code followed by the fork call. Because we are inside a scoped value.where block, these virtual threads automatically and efficiently inherit the user context without the memory overhead of thread local.
Category 8 Conclusion. The reality of millions of threads.
Virtual threads have fundamentally changed the economics of Java concurrency, but as we've seen in these incidents, they do not grant immunity from the laws of physics. Pinning carrier threads with legacy synchronized blocks or exploding memory with millions of thread local instances will bring down even the most modern Java 21 environment. Mastery in the Loom era means moving from thread management to backpressure management. By enforcing structured concurrency and protecting your carrier threads, you enable your platform to reach scales that were once only possible in low-level languages.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 8 to Category 9.
But even if your threading model is perfectly fluid, your application is only as fast as its compiled machine code. If virtual threads are the skyscrapers, then the JIT compiler is the foundry that forged the steel. When the code cache fills up or the JIT de-optimizes due to profile pollution, your performance does not just dip. It reverts to the slow, interpreted world of 1995. We now move from the orchestration of threads to the actual forging of performance. Code cache, JIT compiler, and GraalVM incidents. Let's explore Category 9.
Category 9. Code cache, JIT compiler, and GraalVM incidents.
The just-in-time JIT compiler and the modern GraalVM ecosystem are the secret weapons behind Java's enterprise dominance. In this category, we dive into the high-stakes world of code cache exhaustion, where the compiler simply stops working, and the de-optimization storms that occur when the JVM's performance assumptions are shattered. We test your ability to tune the foundry of your application, from tiered compilation to the closed-world constraints of GraalVM native images.
Category 9. Compiler and GraalVM Production Incidents, 117 to 125.
Here are the 9 incidents covering JIT collapses and GraalVM migration disasters. Production Incident 117. Code cache exhaustion causing the JIT compiler to stop completely. Production Incident 118. Excessive JIT compilation CPU spikes following a large-scale deployment. Production Incident 119. JIT de-optimization storm triggered by profile pollution in a polymorphic gateway. Production Incident 120. Performance regressions during the migration from Hotspots C2 to GraalVM JIT. Production Incident 121. Inconsistent warm-up behavior caused by misconfigured tiered compilation flags. Production Incident 122. Runtime failures in GraalVM native image due to missing reflection configurations. Production Incident 123. Native image size bloat and unexpected slow cold starts in serverless functions. Production Incident 124. Compiler thread exhaustion during heavy dynamic class loading events. Production Incident 125. Behavioral differences between AOT and JIT affecting GC and memory patterns. Total 9 incidents for Category 9. Let's start with the silent freeze of Production Incident 117.
Production Incident 117. After 3 months of continuous uptime, your global trading gateway experienced a sudden, inexplicable 10 times increase in latency. Monitoring shows CPU usage is low, but the JIT compiler has stopped generating native code because the code cache is 100% full. How do you recover and resize the cache?
Answer: this is a compiler stall incident. Once the reserved code cache size is reached, the JVM disables the JIT compiler and reverts to interpreted mode. I would resolve this as follows. 1. Immediate action. Check the logs for code cache is full. Compiler has been disabled. Since the JVM cannot re-enable JIT without a restart, you must perform a rolling restart of the cluster to restore native speed. 2. Tuning fix. Increase the -XX reserved code cache size to 512 megabytes or 1 gigabytes. Large monolithic applications with thousands of classes often exceed the default 240 megabytes limit. 3. Optimization. Enable -XX plus segmented code cache default in Java 9+. This divides the cache into non-method, profiled, and non-profiled segments, allowing the JVM to manage memory more efficiently and prevent fragmentation. 4. Governance. Implement a code cache usage alert in your APM. If usage exceeds 80%, it's a signal to increase the cache size or investigate why so many unique methods are being compiled. Pro tip: interpreted mode is the silent killer of Java performance. If your code cache is full, your 10 milliseconds app becomes a 100 milliseconds app instantly. Always set your reserved code cache size explicitly for large enterprise jars. Here is JVM configuration, demonstrating how to monitor and size the reserved code cache to prevent JIT compiler shutdowns. Disclaimer: always test code in a non-production environment. This code, followed by the size flag, expands the memory pool for JIT compiled native code. For large microservices, doubling the default value prevents the compiler from giving up after months of uptime. Here is the code followed by the print flag. This ensures that the JVM outputs the final state of the code cache upon exit, providing the forensic data needed to tune the size for the next deployment.
Production Incident 118. Within 60 seconds of a new deployment, your customer portal cluster hit 100% CPU on all nodes. JFR Java Flight Recorder shows that 80% of CPU cycles are being consumed by JIT compiler threads. Why is the compiler storm happening, and how do you protect your startup?
Answer: this is a warm-up saturation failure. When a fresh JVM receives peak traffic, the JIT C1 and C2 identifies thousands of methods as hot simultaneously and attempts to compile them all at once, starving the application of CPU. I would immediately implement a warm-up phase using a Kubernetes startup probe to send dummy traffic before the node joins the load balancer. For a permanent fix, I would use the -xxci compiler count flag to limit the number of background compiler threads, ensuring the JIT cannot hijack the entire CPU and crash the node during the ignition phase. Pro tip: high CPU at startup is expected, but CPU starvation is a bug. Limit your CI compiler count to 2 or 4 on small containers to ensure your business logic always has at least 50% of the CPU during the warm-up storm.
Production Incident 119. Your Universal Payment Gateway accepts 50 different payment methods via a single interface. After adding the 51st provider, the JIT compiler de-optimized the core processing method, and latency jumped by 500%. What is profile pollution, and how do you fix it?
Answer: this is a megamorphic call site failure. The JIT optimizations like inlining only work well if a call site sees one monomorphic or two bimorphic implementation types. When you hit the megamorphic threshold, typically 3+ types, the JIT gives up on inlining and reverts to a slow virtual table lookup. I would immediately refactor the gateway to use a dispatch map or chain of responsibility where each call site only interacts with a specific implementation type, or increase the -xx max inline level to attempt deeper optimization, effectively restoring the inline speed by helping the JIT see through the abstraction. Pro tip: JIT compilers hate interfaces with 100 implementations. If your core loop is megamorphic, the JIT cannot optimize it. Use direct type checks or factory dispatchers to keep your hot paths monomorphic and JIT friendly.
Production Incident 120. You migrated your data processing cluster from the standard Hotspot C2 compiler to the GraalVM JIT Compiler Enterprise Edition. While most of the app is faster, your string-heavy regex engine is now 30% slower. How do you troubleshoot a cross-compiler regression?
Answer: this is a compiler heuristic mismatch. GraalVM and C2 use different logic for inlining and partial escape analysis. I would resolve this as follows. 1. Diagnosis. Use the GraalVM IGV ideal graph visualizer to compare the compilation graphs between C2 and Graal. Look for inlining failures in the regex utility methods. 2. Tuning fix. Use the -dgraal.compiler configuration equals enterprise or community flags to adjust the optimization level. Often, Graal is over-optimizing certain paths, leading to longer bailout times. 3. Code optimization. Refactor the regex code to be Graal-friendly by reducing the use of final fields in ways that confuse Graal's partial escape analysis. 4. Verification. Use -xx plus print compilation to ensure the most critical methods are being compiled by the Graal level 4 engine rather than staying in C1 level 3. Pro tip: GraalVM is superior for modern, highly abstracted Java like Scala or Streams, but legacy C-style Java code often performs better on C2. Always benchmark your specific workload before switching compilers.
Production Incident 121. Your real-time fraud service shows inconsistent warm-up. Sometimes it reaches peak speed in 2 minutes, other times it takes 20 minutes. You discover that tiered compilation is getting stuck in level 3C1 with profiling. How do you force a faster ignition?
Answer: this is a profiling queue bottleneck. Level 3 requires the JVM to collect execution data profiling before moving to level 4C2. If the profiling queue is full, the JVM stops promoting methods. I would immediately increase the -XX tiered compilation queue threshold or decrease the -XX tier 3 invocation threshold to force the JVM to move code to C2 much faster. I would also check for compiler thread starvation incident 124 to ensure that the threads responsible for level 4 compilation are not being blocked by other system tasks. Pro tip: tiered compilation is a pipeline. If level 3 is slow, level 4 never happens. Use jstat-compiler to see if your tier 4 count is growing. If it is stuck, your thresholds are too high for your traffic volume.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 122. After deploying your first GraalVM native image for a serverless function, the application crashes at runtime with a class not found exception when trying to deserialize a JSON payload. Why did the native image fail to find a class that clearly exists in the project?
Answer: this is a closed world violation. GraalVM native image uses static analysis at build time to remove unused code. Because JSON deserialization uses reflection to find classes at runtime, the Graal compiler threw away those classes during the build, thinking they were unused. I would resolve this by providing a reflect-config.json file that explicitly tells the Graal compiler to preserve these classes for reflection. To automate this, I would use the GraalVM tracing agent in a standard JVM run to automatically generate the required JSON configuration based on actual application behavior. Pro tip: in native image world, reflection is invisible. If your code uses class dot for name or any dynamic mapping, you must declare it at build time. Use the native image agent to catch these missing reflection errors before you deploy to production. Here is a GraalVM reflection config.json, demonstrating how to explicitly preserve classes for runtime reflection in a native image environment. Disclaimer: always test code in a non-production environment. This code, followed by the class name, tells the GraalVM static analyzer that this specific class must be included in the native binary, even if no direct code references it during the closed world analysis.
Production Incident 123. Your AWS Lambda Java function is suffering from cold start latency of 8 seconds despite using GraalVM native image. You find that the binary size is 250 megabytes, and the function is spending 5 seconds just loading the binary into the Lambda environment. How do you slim down the native image?
Answer: this is a native bloat incident. A large native binary defeats the purpose of serverless speed. I would optimize the image size as follows. 1. Analysis. Use the -h plus print analysis mesh flag to see which transitive dependencies are dragging in unnecessary classes, for example, pulling in all of Netty for a simple HTTP client. 2. Remediation. Use selective dependencies. Replace heavy libraries with native-first alternatives like Micronaut or Quarkus, which are designed to minimize the closed world footprint. 3. Optimization. Enable -ob optimize for size or use the G1 garbage collector for native image enterprise, only which can sometimes result in more compact binaries. 4. Result. Reducing the binary to 50 megabytes will cut the load time from 5 seconds to 500 milliseconds, finally achieving the instant start goal of serverless Java. Pro tip: native image does not automatically make your app small. If you include a heavy framework like Spring Boot without native-specific optimizations, your binary will be massive. Use native build profiles to strip the bloat.
Production Incident 124. During a dynamic plugin loading event, your JVM became unresponsive. You find that compiler threads are at 100% and are blocked. How do you diagnose compiler thread exhaustion during heavy class loading?
Answer: this is a metadata compilation deadlock. When thousands of classes are loaded dynamically, for example, via OSCI or dynamic jar loading, the JIT attempts to compile the constructor and initializer for every class simultaneously. I would immediately increase the -xxci compiler count to handle the burst. However, if the threads are blocked, it's likely a metaspace lock contention. I would refactor the plugin loading to be serial or chunked rather than parallel, ensuring that the JIT compiler can keep up with the class definitions without creating a massive backlog of pending compilation tasks. Pro tip: class loading is a synchronized operation in many JVM parts. If you load 10,000 classes in 100 threads, you will spend more time waiting for the metaspace lock than actually loading classes. Keep your class loading sequential for better JIT stability.
Production Incident 125. You notice that your GraalVM native image uses 40% more RAM than the same app running on Hotspot JIT once it reaches peak load. Why does AOT ahead of time code sometimes have a worse memory to throughput ratio?
Answer: this is an AOT optimization limit incident. JIT compilers have the advantage of runtime data to perform optimizations that AOT cannot. I would address this memory gap by 1. Root cause. JIT compilers can perform speculative inlining and uncommon trap optimizations, which results in more compact, specialized native code. AOT code must be more generic to handle all possible paths, often leading to larger code and more object allocations. 2. Tuning. Use PGO profile guided optimization for native image. This involves running the app once to collect a profile and then rebuilding the native image using that data. 3. Result. PGO allows the AOT compiler to perform JIT-level optimizations, reducing the memory footprint and increasing throughput by 20 to 30%, matching the efficiency of Hotspot. 4. Governance. Never deploy a raw native image for high-throughput production. Always use PGO to bridge the performance gap between AOT and JIT. Pro tip: native image without PGO is like a JIT without profiling. It is fast at startup, but it will never reach the peak efficiency of a warmed-up Hotspot JVM. For production, PGO is mandatory.
Category 9 Conclusion. Mastering the JIT Foundry.
Just-in-time compilation and GraalVM represent the peak of Java's adaptive performance. As we've seen in these incidents, when the foundry of your application, the JIT compiler, is tuned correctly, it can outperform static languages. But when the code cache is exhausted or de-optimization storms occur, your application loses its edge. Mastery here means understanding the contract between your bytecode and the compiler, ensuring that your most critical paths are always forged into high-performance native code.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Transition from Category 9 to Category 10.
But even the most optimized machine code is only as good as the artifacts that contain it. If the JIT is the foundry, then your dependencies and class loaders are the supply chain. When your build pipeline introduces duplicate jars or your class loader hierarchy leaks, the resulting jar hell can cause inconsistent behavior that only appears under production pressure. We now move from the binary compiler to the organizational complexity of dependency, class loading, and build pipeline incidents. Let's explore Category 10.
Category 10. Dependency, class loading, and build pipeline incidents.
Dependency management is the silent architect of enterprise stability. In this category, we explore the war stories of metaspace bloat caused by duplicate classes, the circular logging loops that crash CPUs, and the breaking changes of the Java module system, JPMS. We test your ability to debug the invisible conflicts that occur when multiple versions of the same library collide in your production class path.
Category 10. Dependency and class loading production incidents, 126 to 131.
Here are the 6 incidents covering jar hell and build pipeline failures. Production Incident 126. Class loader leaks in a dynamic plugin system, preventing metaspace reclamation. Production Incident 127. Duplicate classes and jar hell causing inconsistent production behavior and metaspace bloat. Production Incident 128. Multiple logging framework conflicts causing CPU spikes and missing telemetry. Production Incident 129. Slow class path scanning with thousands of dependencies delaying critical scaling events. Production Incident 130. Shading and dependency version conflicts appearing only in high-load production environments. Production Incident 131. Java module system, JPMS access violations following a mandatory JDK upgrade. Total 6 incidents for Category 10. Let's start with the memory leaking class loaders in Incident 126.
Production Incident 126. Your real-time analytics platform allows hot redeployment of custom logic jars. After several redeployments, the JVM crashes with Metaspace despite having 2 gigabytes of free heap. You find that thousands of old class loaders are still in memory. How do you resolve the class loader leak?
Answer: this is a class loader retention failure. A class loader cannot be garbage collected as long as one of its classes or a static field in the host app holds a reference to it. I would resolve this as follows. 1. Diagnosis. Use Eclipse Mat to find the path to GC root for the leaked class loader. Look for static references or thread local variables that were not cleared by the plugin during the unload event. 2. Immediate fix. Increase -XX max metaspace size to delay the crash, but initiate a code audit on the unload lifecycle immediately. 3. Remediation. Implement a cleanup hook in your plugin manager. Ensure that all listeners are unregistered and all static collections containing plugin-provided classes are cleared or nulled out. 4. Governance. Use a weak reference for any registry that stores plugin-provided objects, ensuring the GC can reclaim the class loader even if the host app forgets to unregister it. Pro tip: class loader leaks are usually caused by static sticky references. A single static list of plugin callback in your host application will keep every version of every plugin you ever loaded in memory forever.
Production Incident 127. A payments microservice is behaving inconsistently across different pods. Pod A is using the 2023 security library logic, while Pod B is using the 2026 version, leading to intermittent transaction failures. You discover that both versions of the jar are present in the class path. How do you resolve jar hell?
Answer: this is a class path ordering non-determinism. When two jars contain the same class name, the JVM simply picks the one it finds first on the disk. I would immediately implement an enforcer rule in Maven or Gradle to fail the build if duplicate classes or overlapping jars are detected. I would then use the mvn dependency tree or Gradle dependencies command to find the transitive dependency that is sneaking the older version into the build. By adding an exclusion to the build script, I ensure that only one unambiguous version of the security library exists in the final deployment artifact. Pro tip: jar hell is a silent killer. If you have duplicate classes, your application behavior depends on the file system order of the OS. Always use the Maven Enforcer plugin to guarantee that your production class path is clean and unique. Here is Maven configuration, demonstrating how to use the Enforcer plugin to prevent duplicate dependencies and jar hell in your build pipeline. Disclaimer: always test code in a non-production environment. This code, followed by the convergence rule, ensures that every dependency in your project and its sub-dependencies settles on the exact same version, preventing the version drift that causes unpredictable production behavior.
Production Incident 128. Your order processing service suddenly stopped outputting logs, and CPU usage jumped by 15% on all nodes. You find that the app has both log4j over SLF4j and SLF4j over log4j on the class path, creating a recursive logging bridge. How do you break the loop?
Answer: this is a logging bridge deadlock. The two bridges are forwarding calls to each other in an infinite circle. I would resolve this as follows. 1. Immediate action. Identify the bridging jars in your deployment artifact, usually log4j over SLF4j.jar and SLF4j log4j12.jar, and remove one of them immediately. 2. Root cause analysis. A third-party library likely brought in a legacy logging binder that conflicted with your modern SLF4j setup. 3. Remediation. Standardize on one implementation, for example. Logback and use Maven exclusions to block all other logging binders like Commons logging or java.util.logging from the final package. 4. Governance. Implement a logging policy that forces all dependencies to use the SLF4j API and only provides the implementation logback or log4j2 at the highest level of the application module. Pro tip: logging bridges are meant to help, but having both ends of the bridge will crash your JVM. Always pick one logging implementation and exclude the rest from your transitive dependencies.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect, We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Production Incident 129. During a critical scaling event, your checkout service took 4 minutes to start because of classpath scanning. You find that the application has 3,000 jar dependencies, and Spring is scanning all of them for annotations. How do you optimize the build for fast ignition?
Answer: this is a dependency saturation failure where unused jars are tax on startup time. I would optimize the build as follows. 1. Clean the build. Use the Maven dependency plugin to analyze and remove unused declared dependencies, often reducing the jar count by up to 50%. 2. Explicit scanning. Refactor that component scan to point only to specific sub-packages rather than the project root, preventing the JVM from opening thousands of irrelevant jars. 3. Static indexing. Implement the Spring context indexer at build time to generate a static components file, making the runtime bean discovery big O of 1 instead of big O of n. Pro tip: every jar on your class path is a startup tax. If you do not use it, lose it. A clean dependency tree is the difference between a 30-second and a 4-minute Kubernetes scaling event.
Production Incident 130. You used shading fat jar to resolve a version conflict with a common JSON library. However, in production, certain reflective calls inside a framework started failing with no such method error. How do you debug shading conflicts?
Answer: this is an obfuscation collision incident. Shading renames classes to avoid version conflicts, but it can break reflection if the framework expects the original class name. I would resolve this as follows. 1. Root cause. The Maven Shade plugin was configured to relocate the library, for example, com.google.json leads to shant.google.json, but the framework was looking for the hard-coded string com.google.json.json via reflection. 2. Remediation. Exclude reflective classes from the relocation rule or update the framework configuration to use the new shaded class path. 3. Alternative. Move to a BOM bill of materials approach for dependency management instead of shading, forcing all modules to use the same compatible version of the library across the entire enterprise. 4. Verification. Use jar-tf-app.jar to inspect the contents of the final artifact and verify that the relocation matches your expectations and the framework's requirements. Pro tip: shading is a brute force solution for jar hell. It works for private libraries, but it often breaks public SPIs and reflection. Use dependency management first, only shade as a last resort. Here is Maven configuration, demonstrating how to use the Shade plugin's relocation feature to isolate conflicting library versions. Disclaimer: always test code in a non-production environment. This code, followed by the relocation pattern, renames the entire library's package at the bytecode level. This allows your app to use one version, while another dependency uses a different version without a class path collision.
Production Incident 131. After a mandatory upgrade to JDK 21, your core crypto library is failing with an inaccessible object exception. You find that the library is attempting to access private fields in the Java.base module, which is now blocked by the Java Module System, JPMS. How do you bypass strong encapsulation?
Answer: this is a JPMS enforcement failure. Modern JDKs 17 plus strictly enforce strong encapsulation, meaning even reflection cannot access internal JVM classes without permission. I would immediately add the --add opens or --add exports flag to the application startup script to puncture the module boundary and allow the legacy crypto library to function. Long term, I would work with the library vendor to migrate to public APIs or find a modern replacement that respects JPMS boundaries, as the bypass flags are a technical debt that makes future JDK upgrades even harder. Pro tip: the --add opens flag is an escape hatch. It should only be used as a temporary bridge during migration. If your architecture relies on hundreds of these flags, you are fighting against the security and performance benefits of the modern Java platform. Here is JVM configuration, demonstrating how to use the --add opens flag to bypass JPMS strong encapsulation for legacy reflective libraries. Disclaimer: always test code in a non-production environment. This code, followed by the open command, grants deep reflection access to the java.lang package. This is the secret sauce that allows legacy frameworks to continue working on modern, secure JDKs until the code can be properly refactored.
Category 10 Conclusion: Securing the application supply chain.
Dependency and class loading management is the final layer of internal JVM stability. As we've seen in these incidents, jar hell and class loader leaks are not just build time inconveniences. They are production vulnerabilities that cause non-deterministic behavior and silent memory bloat. Mastery here means moving beyond "it works on my machine" to enforcing strict dependency convergence and understanding the module boundaries of the modern JDK. By securing your application's supply chain, you ensure that the code the JIT compiles is exactly the code you intended to run.
Part 1 Conclusion: The engine is forged.
We have now completed our deep dive into the engine room of the Java virtual machine. Across these first 131 production incidents, we have mastered the internal mechanics of the managed heap, the metabolic cycles of the garbage collector, the precision of thread orchestration, and the adaptive power of the JIT compiler. You now possess the forensic skills to diagnose any failure that occurs within the boundaries of the Java process itself. You are no longer just a developer. You are a JVM performance engineer.
Transition to Part 2: From the process to the perimeter.
But even a perfectly forged engine will fail if it is placed in a hostile environment. A JVM does not exist in a vacuum. It lives inside a Kubernetes container, communicates over a congested network, persists data to high-latency disks, and interacts with distributed systems like Kafka and Postgres. To be a true staff-level engineer, you must look beyond the Java process and understand how the JVM interacts with the wild. We must now move from the internals to the infrastructure. Let's prepare for Part 2.
Part 2: The Enterprise Frontier. Categories 11 to 2079 Incidents.
In the second video of this masterclass, we will explore the final 79 production incidents across these 10 external domains. Category 11: Kubernetes and Container JVM Incidents Limits, Probes, and Evictions. Category 12: Kafka and Messaging Performance Incidents Lag, Rebalances, and Batches. Category 13: Database and JDBC Performance Incidents Pools, Latency, and Leakage. Category 14: Reactive Systems and Async Pipeline Incidents, Backpressure, and Starvation. Category 15: Observability and Monitoring Incidents, APM Overhead and Cardinality. Category 16: Network, OS, and Socket Level Incidents, Port Exhaustion, and TLS Overhead. Category 17: Security and Cryptography Performance Incidents, Encryption, and Handshakes. Category 18: Hardware level and extreme low latency incidents, NUMA, and cache lines. Category 19: Disk I/O, file descriptors, and file system incidents, I/O weight and bloat. Category 20: Cloud, resource, and hardware management incidents, throttling, and noisy neighbors. 79 high-stakes scenarios remain to complete your mastery of the Java ecosystem. The journey into the enterprise perimeter continues in Part 2. You can find the link to the next video in the description below. I'll see you in the next war room.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers. For 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.